out-of-the-box geometric computing with Python course, from theory to practice. If you want to see the course notes and all the material for this course, please check it at the URL in the slide or in the comments below. So this is a course presented by Sebastian, which works at TU Berlin, and Teseo, Chen, and me, I'm Daniele, from New York University. The goal of the course is to teach you how to design, program, and analyze algorithms for doing geometric computing. And in particular, we will give you hands-on experience with shape modeling and geometry processing algorithm by, during the entire course, showing you live demos. And you will see in a second that you can also access the same material and run it on your machine as you follow the videos in this course. And a focus of the course will be on learn how to do batch processing of large collection of geometric data to use it for deep learning pipelines. First of all, what is geometric computing? It's a field that is in between discrete differential geometry that focuses on representing surfaces and volumes, and just a few lines of code. Another one is libigl. This is a library that has been developed for many years. It contains a large collection of geometric processing algorithms, and we're going to use extensively this library for doing both loading of meshes and processing, and there is going to be an entire section dedicated to libigl. Then wild meshing. This is an open source library for doing meshing, so for both triangle meshing in 2D and tetrahedral meshing in 3D. It's also this one fully available through Conda, and you're going to see in one of the applications how to use this library to generate your meshes. Finally, Polyfem. This is a library for doing finite element, for doing simulations using the finite element method. And also this one is available through Python, and it will be used in one of the applications. So before we move on to the technical part of the course, I would like to just give an overview of what is the major similarity between all these libraries and everything that you're going to see in this course. And this is a standardized way of transferring data and representing data so that it's possible to move it between different libraries in a seamless way. So let's start with a basic representation for surfaces that we're going to use, which is a triangle mesh, meaning that the surface is divided into triangles, and so it's sampled at a set of points, and these points are connected with triangles. So let's zoom in here. And so now if you look at one vertex, this vertex will be described by x, y, and z coordinates. So we have one set of coordinates for every vertex, and the way we decide to represent all of these is to take all these vertices and put them all together in one matrix that has as many rows as the number of vertices and 3 columns, one for all the x coordinates, one for y, and one for z. So this is just a n times 3 with n the number of vertices. It's a matrix of real numbers. Now let's go to the faces. So every face is made of 3 vertices, and we're going to identify it by storing the 3 indices of the vertices. And in this case, the orientation matters. We have a convention that using the right-hand rule, we want this vector to point outside the surface so that we fix this orientation consistently for all the vertices of a mesh. So after we have these, we're going to have many faces to store. And so for every face, we have a set of indices. And so similarly to what we did before, we place all these indices in one single matrix that has size m times 3, where m is the number of rows and is the number of triangles. And we have 3 columns, one for every one of the indices. And so now the entire mesh is represented as 2 matrices, one that stores the coordinates and one that stores the indices into the matrix of coordinates. So why do this? Like, why using just raw matrices to store the data? So there are many reasons for this. One is that it's memory efficient and cache friendly. This is a very simple representation. Every time you read a number, you're gonna read a few, all the one that fits in your cache line, and in this case it's going to be a few numbers that are actually useful for subsequent computations. One major practical advantage, practical from the point of view of people developing algorithms, is that indices are so much easier to debug than pointers. So in our case, when you have these 2 matrices, you can just plot them in a terminal for a small mesh, and you can look at them and you can make sense of it. Since they are simple, they are trivial to copy and to serialize, meaning that most libraries use matrices, and so as long as you use a standard format, it's very easy to save a matrix and load it somewhere else. So this makes our algorithm interchangeable with many other libraries. For example, if our decision for this course is to use NumPy as the common denominator for exchanging data between different libraries, and this allows the libraries that you saw, like libigl and Polyfem and wild meshing, to directly be usable in an application written in PyTorch and directly exchange data with it, because all the data is represented in NumPy format. Or similarly to TensorFlow, or if you want to use some function in SciPy, or even externally to Python, you can save it to a file and load it back on MATLAB or do some processing with OpenCV. So this concludes the introduction, and we are now going to continue with an introduction to finite elements.
Welcome everybody to the Introduction to Finite Element tutorial. I will be following and giving this tutorial on a Jupyter notebook. If you want, you can go online and modify and follow the tutorial directly from Binder. Binder is a nice service where you can actually run a notebook directly live without needing to install in Python or the notebook itself. The link is on this slide. You can also open it through the QR code. So let's start. The goal of finite element is to solve a partial differential equation, a PDE, on a domain omega. So for this tutorial, I will be picking the simplest possible PDE, which is Laplacian of u equals 0. And to simplify things further, I will just consider the domain to be in 1D. So in 1D, the Laplacian, which is the sum of the second derivative, is just the second derivative of the function u. Now this equation is weird because the unknown is not anymore a number, but it's a function itself. And we can think about which function u satisfies this equation. And one simple one is u of x equals 0. Of course, the second derivative are 0, and it satisfies this PDE. Another one is u of x equals x. In this case, too, the second derivative are 0, and it also satisfies the PDE. So from this simple example, we can see that just having the PDE is not enough. And in general, when you have a PDE, we have something else associated with it, which is the boundary condition. And the boundary condition will tell us what is the behavior of the function u that we want to have on the boundary of the domain omega. So for the super simple case in 1D, the boundary is just the two-end point of our domain. Our domain will be a line. So what we want to do is specify what is the value of the function u at the first point of the interval and the last point of the interval. So for example, if our domain is the interval 0, 1, well, we want to know the value of the function u at 0 and at 1. So for example, if we say, well, u of 0 equals 0 and u of 1 equal 1, at this point we have only one solution, which is u of x equal x. It satisfies both the PDE and the boundary condition. Now in finite element, instead of directly solving this Laplacian of u equals 0, which is a complicated function, we have a unknown, which is a function, and we have only one equation. The idea is to multiply this equation left and right with some test function v, and then take the integral. This different form is called the weak form of the original PDE. Now this has two main changes. The first one is we started with one equation and now we have infinitely many. The second one is that the initial equation required the function u to be twice differentiable, the Laplacian needed to exist, and now we only require that the second derivative to be integral. It's a little bit weaker. What's nice about this weak form is that there are important theorem that says that if the weak form holds for any test function v, then u is also a solution of the original PDE, which is also called the strong form. So now we manipulated our initial equation and we obtained another equation which has the same solutions. And now we can start trying to manipulate this integral to make it simpler. So if we go back to high school math, you probably have done integration by part a lot. So what we can do is just use this integration by part theorem. There is a link on Wikipedia. You can just do integration by part and you end up with this formulation. Now if we assume, for example, that our test function v is 0 on the boundary where the function u is known, which is completely possible, we end up with this yet another simplified version. And here again, the big difference from the initial equation to the last one is that now we require only the gradient of the function u to be integrable. We don't require the second derivative to be integrable. And for example, a piecewise linear function is obviously not C1. The gradient of a piecewise linear function is piecewise constant and is not continuous, but is obviously integrable. We can integrate a piecewise constant function. So now we have this equation, which is simpler than the one in the beginning, but still we don't know how to solve it. So if we want to actually solve this equation with a computer, what we need to do is discretize our function u with a finite dimensional basis. Or in other terms, we can project our continuous smooth function into a finite dimensional space. And the idea here is pretty similar to what we do with a vector in R3. So in a vector in R3, we'll have three numbers, 2, 0, 1, and these are the three coefficients we are multiplying the basis vector with. And here is pretty similar. Instead of having basis vector, we'll have a basis function phi, we'll have n of them, and then we will have some coefficient ui, which will be multiplying the basis function with to obtain our function u. What's super important here to note is that now we only need to find the coefficient ui, but even if now we need to find a discrete number of values, the ui's, the function u is still a continuous function because we're just multiplying these values with basis functions. So now that we have this discrete version, what you can do is just plug it in inside the weak form we simplified before. And now if we swap the integral with the sum, we obtain this new formulation. And this is nice because now the unknowns are not anymore a continuous function, but it's just this coefficient ui. Now another common trick in finite element is that while instead of testing for any function v, we can express v in the same basis as the function u, and then this boils down into replacing for all v into for all test function phi j. So if we also apply this into weak form, we end up in this nice formulation which we can re-express in matrix form. So we have L times u, where u is a vector containing ui equals 0, and L is just this integral of the product of the gradient, the dot product of the gradient of the basis function integrated over the domain. So you see, we started with a complicated problem, which was the Laplacian of u equals 0, and the unknown was a function which we even didn't know how to represent, and by manipulating integral and introducing a finite dimensional function space, we end up with solving a linear system, which is something we know how to do. Now that we went through the theory, I can actually show you how to implement that theory and that solving the PDE simply using Python. So for doing that, I will use a couple of standard Python libraries, the first one being NumPy for the algebra. Then I will use SciPy, sparse matrices, because there will be some sparse matrices involved. Then I showed you before there was a linear system, so we'll be needing to solve a linear system, and for this reason I will use SBSolve from SciPy. And finally, to illustrate what's happening, I will use Plotly for plotting. So let me execute this cell here to import the necessary libraries. So now if we want to actually implement that, we need to start picking things. So the first thing we want to do is to pick what is our domain, and here for simplicity the domain will be the interval 0, 1. And then we want to discretize this domain into an L segment, so some segment or element Si. So how we do it with Python? Well, we just define a domain as an NumPy array 0, 1, then we just pick the number of element, which is 10. The number of bases we will have in our finite element space will be n element plus 1, which is the number of nodes, which is 1 plus 1. And then just using some linear space, we can actually get the elements, and then at the very end I can plot them just to show you what's happening. So here is our segment from 0 to 1, and you see here there are 10 different segments and we have 11 nodes. So I just want to say something regarding this step. This step is what's usually called meshing. So in 1D it's extremely simple, you just need to chop it into segments. In 2D and 3D it's become more complicated. We have our complex domain, which is a shape or a volume in 3D, and now we need to decompose it into triangle or tetrahedron or hexes. Anyhow, we need to split it into a finite element and find a number of pieces. So now that we have this element, what we can do is simplify our integral further. So if you remember, we had this integral over the domain omega, and there is another fundamental theorem of integral, is that if we have a non-overlapping covering partition of the domain omega, we can actually split the integral over all the pieces. So this is just fancy word for saying instead of integrating over omega, now we can we can integrate over every element SE and just take the sum. And this is valid because all the elements cover the original domain and they are not overlapping. These two are completely equivalent. So now we end up having an integral over the single pieces, over the single elements. So now we need to pick what the basis functions are, and one simple way of defining basis function is we want to have something that's interpolatory. So we want a basis function which is 1 over an element and 0 everywhere else. I just want to point out that this is just a simple standard choice. It can deviate. For example, if you're doing IGA, you will have bases which are not interpolatory. There is no strict requirement of interpolation. So let me show you how the basis function should look like. So let me run this notebook. So here is all the basis functions, so it's a bit confusing. So I can try to hide some of them. So for example, here you see that the red one or the blue one at the very end is 1 over the node which is 1 and 0 everywhere else, and same holds for the red one. We can look about something interesting here. If I now zoom over an element here, this element here, we see we have only two non-zero basis functions, the red one which is going down and the green one which is going up. And this is true not only for the for that pair, it's true for any pair. If I zoom here over another element, we have the pink one which is going down and this other green which is going up. And all elementary kind of look similar. This is an important consideration in finite element because it allows to localize the whole thing. So the idea now is that instead of defining this basis function globally like I did before, we can define them locally on a reference element which is the same for every element. So since we need to choose and we are completely arbitrary in the choice of the reference element, we can literally pick anything. So the idea is to pick something that makes our life simple. So this reference element as hat in this case will be the interval 0, 1. So in 2D we will have a reference triangle, and again for simplicity we will be picking something like a right angle triangle on the origin. And in 3D we will have this regular tetrahedron which is formed by the three 1, 0, 0, 0, 1, 0, and 0, 0, 1 axis and have this diagonal face. So let's stick to 1D. So we have this super simple segment of unit length. And on top of this segment we saw before with the zoom in, we will have only two non-zero local bases. So there will be two pieces defined on S hat. And one will be the one going up and the other one will be the one going down. And since we decide the reference element to be this unit segment, we can actually hardcode and define what are the bases. So we have one which is the phi 0, which is just 1 minus x. This is the one which is 1 at 0 and 0 at 1. And the other one is just the x function. And you see here the nice part about having this reference element is we can literally hardcode that stuff, and this simplifies everything a lot. So we can try to plot them to see if it looks like it should be. So here we have only two, one which is the one going down in blue, and the other one is the one going up. And here we have coded the reference element, which is just the segment 0, 1. So now that we have this reference element, what we need to do is to take every individual segment, SE we had in the very beginning, and map them to our reference element. So this is not particularly difficult in 1D, and this is called a geometric mapping. So what we need to do is we have our segment 0, 1. What we need to do is shift it according to the start point of every segment and then scale it. For example, if our segment is if the actual segment is segment 0.1, 0.2, we need to scale it by 0.1 and then move it by 0.1. So this is also similar in 2D and 3D. So in this case we will have an affine transform which transform our reference element, our, for example, right angle triangle, to any triangle in our mesh. In this case it's way simpler. So now we have a geometric mapping, so we know how to map from the reference element to the actual element. A super important property of this geometric mapping is that it needs to be bijective. We need to be sure we can map bijectively our reference element to any element in the mesh. And this is related to the, in 1D is simple, but if we ever try to do a mesh, you don't want to have a flipped element. You want to all your element to be positive. And this is the positivity of or not having flipped element is a fundamental requirement to have this geometric mapping being bijective. So now that we have our reference element, what we can do is to try to modify yet again our integral to be able to integrate over the reference element. So what we will be doing here is use again high school math, which is the change of variable in integral. Here it becomes a little bit more complicated because we have more integral and more stuff in, but this is really straightforward and simple. So what I just want to note is that when we change the integral from integrating over an element SE to the reference element, there is G prime here appearing, which is the change of scale of the element from the actual element to the reference element. In 2D and 3D, everything becomes more tedious because the gradients here are the gradients are not just first derivative, are just actual gradients, so they're vector, and this G prime is not anymore just a G prime, it becomes the Jacobian of the geometric mapping. It's a bit more complicated, but again, there is a link on Wikipedia you can follow to try to understand how to do it. So now we have this integral, and we can try to do a little bit more. So we add this phi of the geometric mapping of x hat, and if we manipulate and look exactly what it is, this is just evaluation of the basis function on the reference element. So this basis function we defined before. So the gradient of the geometric mapping is just since the scaling doesn't, since the translation doesn't play a role, it's just the scaling here, and then the gradient of the basis function with respect in the global coordinate can be expressed in the local coordinate with the gradient of the basis function on the reference element. So these are pretty straightforward. They are not so difficult to show. I just want to gloss over. So if we just use these three facts, we can apply them in this equation and replace everything with something that's extremely simple. So we have this gradient of the basis function and the gradient of the geometric map appearing. We can simplify and we end up with this really simple formula. Continuing, we can try to see if we can localize this integral even more, because here we had all this sum over all elements, but we saw before that most of them are zero. So how can we actually make it nicer? So what you can try to exploit is the fact that we know that there are only two non-zero bases there, and the only thing we need to be careful is, since we have two non-zero bases, we need to be careful of where these two non-zero bases will be mapping in the global position in the global nodes, and this mapping is called local to global, and it's just mapping the local index 0 or 1 to the actual real 3D node. So what we'll have here is this local to global mapping, which I would call GEI, and it maps the local indices 0, 1 of an element E to this corresponding global indices. So we know we have two non-zero bases, so this is why we have only the index I is only 0, 1, and if we use this global mapping, what we need to do, instead of summing over all n, we know most of them are 0, so we only have two which are non-zero, so we can sum over all element and use the local to global mapping to just use only the one which are non-zero. So now, instead of having a sum of n and then a sum over element, now we only need to sum over the element, and for all elements, we only need to compute a sum over two things. So now everything is nice and localized. So now the only missing piece we needed is we had in the previous formula the gradient of the basis function. So if you remember, the basis function was 1 minus x and x. And now again, since we have coded everything, and this is what we wanted to do to hard code everything, we just need to compute the gradient, which is just minus 1 and 1. Here it just seems a little bit more fancy, and the reason why is I just want to have gradient which respect the shape of the input, so I would be using NP1s and minus NP1 for the two gradient, but this is just an implementation problem. So now that's it. Now we can actually start constructing the bases. So for every element, what we need? We need the number of non-zero bases, which is always 2, the two function of the two gradient, which we defined before, the local to global mapping, which maps the local node 0 or 1 to the global nodes, and the geometric mapping in its gradient. So in this case, in 1D, it's extremely simple. So the local to global mapping is just the index of the element plus I. So for example, the first element, index 0, will have the global node 0 and 1. The first element, which will have index 1, will have the global node 1 and 2, and so on. So in 2D and 3D is similar. You can actually use the vertices, the idea of the vertices of the mesh to represent the local to global mapping. So now that we have all these pieces, we can actually implement. So we'll have an array of elements, and we'll just do a loop for every element. So every element will be this dictionary. And on the dictionary, I will store the number of non-zero bases, which is 2 here. Then I will store the two basis function, which is the two basis function on the reference element, which is phi0 and phi1, and their gradient. the local to global mapping we saw before, which is E and E plus 1, and then the geometric mapping, which I will be storing as a function. So it's a function that takes x, and here in this case it's just a scaling, and for the gradient of the geometric mapping it's just a scaling, and just appending everything here. Let me execute this cell. So now we have our element. So now we can use our element before going into the solving the PDE. We can use our element to interpolate a function given in global coordinate. So let's try to think about how we can do it. So since everything is defined with respect to the reference element, what we need to do is to sample the reference element with an in-space, for example, which will be points where we want to evaluate the local basis. And then the only thing we need to do locally is just compute this sum of from 0 to 1 of ui at the global indices, multiply with the basis function evaluating this x hat lin space. And then we can also use the geometric mapping to compute the position of x at the global in the global positions. So this is the function. So I'm just computing the interpolated function u and the interpolated and the position of x in the global coordinate system. So now I need to sample the reference element, which is this x hat, which is 0, 1, so I just sample many points, and now I just do a loop over every element. So the element we defined before, that were this dictionary. So the first thing, I just grab the element, and then we want to sum the basis function over the reference element. So I just compute this u-log, which is the u computed locally. It's just 0 in the beginning. And now what I need to do is to go over the number of bases, which in this case is 2. If I want to have the global node, I just need to get the global node position I, so this is 1 or 2. And then I just grab the local basis, and what I need to do is just sum over the u local, u at the global node, times the local basis evaluated at this x hat, which is the sampling of the reference element. If I want also, then I just accumulate everything in my global u interpolate. And if I want to also store the global position of x hat, so the image of the geometric mapping, I just need to append to x the evaluation of the geometric mapping at this sample position. And then I just return x and u interpolate. So let me execute this cell. So this is just a function. If you want to try to see what it does, we can just compute some random function u, and this will be just a coefficient, then interpolate and plot. And this is how it looks like. So we had our, here in orange are the value of u, and in blue we see we're using this interpolating basis, and we know the basis is piecewise linear, so we expect to have a piecewise linear function. So what I want to show you here is that if I move the mouse on top of this line, it's not that it's just passing through these two orange dots. There are a lot of many dots, and these many dots are actually the sampling, the lin space sampling of the reference element. So they are linear because they should be linear. It's not that there are no dots in between. So this shows how we can use the finite element basis to actually interpolate values. So now we can go back to our solving the PDE problem, and what we need to do is assemble this matrix L. So assemble is the process of creating the matrix, and this matrix L is called a stiffness matrix. So what we had before, when we were just doing all this manipulation, we had this integral over the reference element of the product of the gradient of the basis function divided by the geometric mapping. The only thing we need to be careful is that we will have these two pairs here, and we need to map them to the global position in the global stiffness matrix using the geometric mapping G. So you see there are some integrals, and there is a way to compute integrals numerically, which is called quadrature. And what's nice about quadrature is if we use a rule which is sufficiently high, we can integrate exactly a polynomial up to that order. And for that, I will just use QuadPy, which is another Python library to do numerical quadrature. So I just create a scheme here. Order 5 is definitely too high, but let's just stick with it. And now, if I want to assemble that matrix, well, what I need to do is, well, I need to create the triplets for creating the matrix, which is row, cols, and vals. And then again, I just need to go over all elements, grab the element. And then if we look back here, we have this integral, which is phi I phi j. So what I need to do is create ij, which is just loop over the non-zero basis. In this case, it would be 2. And then what I need to do is to just compute this integral. And the integral is just the grad phi I times grad phi j divided by the geometric mapping, the gradient of the geometric mapping. And where should I integrate? Well, between 0 and 1, because now we are integrating everything with respect to the reference element. And this will be the value of the integral we have here. And now if we want to put it into global matrix, what I need to do is, well, just use the local to global mapping to decide where it will go in the global position. So I'm just appending the two local indices with the value. And at the very end, I will just transforming these arrays into NumPy's array and then just create a stiffness, the stiffness matrix from the triplets. Execute this. Now we can look at this matrix, and if you ever try to do a finite difference, this is exactly how it looks like. So this is nice because we are back in the things we know. An important difference with respect to finite difference is even if the matrix looks similar, the whole derivation of finite element assumes that this, the solution of the linear system are the coefficient for our basis function. So what we have as a solution is not just the value of the function at certain position at the nodes like in finite difference, but we'll have the coefficient for a continuous function. So the actual solution of a finite element system is a continuous function. Now, well, we just need to set out the boundary condition, so we know the value of the function for the coefficient at 0 at an element, and since the basis is interpolatory, we can just set the matrix to identity. So this is just a fancy piece of code that just kills the first and last row of the matrix and replaces it with 1 and 1. So let me just show you how it looks like. So you see the first row is just an identity, so it's 1 and 0 everywhere, and the last row similarly. And this is just a hack to actually enforce the boundary condition. Since we know what is the value there, if we just put a 1 when we're solving the linear system, we'll obtain what we want. So now we just need to set the right hand side. So the easy thing to do here is, well, we want it to be 0, and then we just want to set to boundary condition. So how we do it, we just create a NumPy array of 0 and set the first and last element, the first one to 1 and the last one to 4. Now, just we want to do is solve LU equal F for U, so we can use this SP-solve to obtain U. Now, that's it. We can use the interpolate function we had before to interpolate the function U everywhere in the domain. Now, before actually executing the cell, I discussed with you in the very beginning that we expect this kind of PD to have a line as a solution. So we want a function where the second derivative are 0. So every linear function has that. And then we want a function which is 1 and 4. 1 at 0 and 4 at 1. So if I plot that, this is exactly what we see. And again, I want to stress here there are many dots in between this orange dot, and this is because we are interpolating this function way denser. Now, before continuing, I want to complicate this problem a little bit more. So we started with this Laplacian of U equals 0, and now what if we want to solve a more complicated PDE, which is called the Poisson equation, and this is just a fancy way to say instead of being equal to 0, we want to be equal to F. And at this point, it becomes way harder to guess what is the solution of this PDE for an arbitrary function f. So one simple thing we can do is assume that the function f is also expressed in the term of the same basis function. So when we, in the very beginning, we multiply our equation by the test function, discretize everything, we can do the same, multiply everything, and now if f is also expressed in the same basis, we end up with this simple equation. So the left-hand side is what we had before, and now we have a non-zero new right-hand side where we have this sum over fi times this integral of phi I phi j. And now we can use the same thing we had before, represent this into matrix form, so we can have Lu equal mf. So L is the matrix we had before, now we have a new m and f. So f is the vector containing the fi, and m is something that's called in the literature mass matrix, and it's just the integral of the product of the basis function. And now we can use the same machinery we did before to localize and do everything and obtain this local mass matrix, which is just the product of the basis function multiplied with the geometric mapping. And now important, there is no division as we had before, and the reason why we had no division is we had division before because there was chain rule appearing. Now we don't have any more chain rule because we are not multiplying the gradient of the basis function, we're just multiplying the basis function themselves. And now what we can do is exactly the same as we did before, but now instead of computing the stiffness matrix, we can compute the mass matrix. And this code is exactly the same. The only line that changes is this one. Now instead of integrating the gradient of the basis function, we're just multiplying phi I with phi j, and we are multiplying with the gradient of the geometric mapping. There is no division. The rest of the code is exactly the same. The only thing that changes is the local value. And like that, we just create the stiffness, the mass matrix. And now we can, for example, set the function f to be 4 and have 0 boundary condition. So we just create a function f, which is just 4 times 1. Then we multiply with the mass matrix and set the first node of f to be 0 and the last node of f to be 0. Now, as before, we can just solve the linear system using SPSolve, and now we can, exactly as before, interpolating the whole system, the function to get the final function. This is something how it looks like. And again, here in between this, it just happens to be linear, but it's because the basis function are linear, but there are many dots. Now, before going to the next part of this tutorial, I just want to show you what happens when the mesh is not uniform anymore. So when we don't have the same number of segments everywhere. So let me go at the very beginning here, where we actually created the mesh, where we discretize our segment with a number of with NL. And we're using a linspace. What we can do is just using something random, and now we have the segments which are not uniform anymore. So if I continue here, the theory is exactly the same, nothing changed. If we try to look at the basis, now they're not uniform anymore. But if we zoom on every one of them, everything kind of looks the same. They're different scale, but they're all the same. We always have this one going up and one going down. Now the difference is just they're not all the same. So the localization is exactly the same. We have the same local basis. This local basis will look exactly the same. We'll have the only big difference, and it's only about the code, is that the local to global mapping will not be the same for all elements because the scaling will be different, but the idea is exactly the same. We'll have this scaling different now for every element, but we still have the same local to global mapping. And then the rest is the same, the change of variable, all the integral manipulation we did. There was no strong assumption to have all the elements exactly the same. So we end up with the same weak form. The local to global mapping is again exactly the same because we are not changing indices here. The gradient of the local bases are the same too. And the assembly is the same. The only difference is now we have this gradient of the gradient of the geometric mapping and the geometric mapping are not the same, but we were not assuming that before, so the code remains the same. Continue here, so we can use the same interpolation we had, and the geometric mapping will take care of the fact that the elements are all different. So if now I run this, you see we still have this function with a lot of value in between. It will still interpolate the orange dot. The orange dot are not uniformly spaced anymore, but it doesn't matter. We still have this piecewise linear function here happening. We can assemble the stiffness matrix using quad pi exactly as before. Everything will be taken care, but now if you look at the matrix, it will look kind of messy because we don't have anymore this uniformly nice spacing, but it's not really a problem. We can still set the first and last row to identity, so we get this identity again, set up the right hand side, solve the problem exactly as we did before, and now we can just plot it, and we obtain the same line as before. It's not that changing the mesh will change the solution of the PDE if the PDE is inside the space of the finite element. So now we have this line, which is not anymore uniformly spaced, but it's still a nice line because the solution of the PDE was a line. And if we want to go with a more complicated problem with the mass matrix involved, it's exactly the same. I'm not changing anything. I'm just re-executing the kernels, just recomputing what is f, solving the linear system again. And now here it will look a little bit different, but it's still, if we continue and create more and more elements here, we'll converge into having this nice smooth function. Okay, that's it. The next step of this tutorial will be moving into, instead of having piecewise linear function, we want to have piecewise quadratic or cubic and so on to have a better approximation of our function. Welcome to the part 2 of the Introduction to Finite Element tutorial. In the first part, we went through the theory and the implementation of a piecewise linear finite element basis. Now I just want to show you that with a little modification, what we can do, we can extend everything to higher order. So as before, I will be using some simple Python library for plotting, for algebra, etc. So let me just execute this. So now what we want to do is exactly as before. We have our domain, which we pick again 0, 1. We discretize it, so we mesh it with an element or segment Si. Now the big difference is that we want to also create some higher order nodes, and this is just a convention or a particular choice in my code here. I will just append the higher order node at the very end. It doesn't really matter where you put the higher order node, it's just important that you remember where these nodes are in the global indices, as we will be seeing. So what we can do, we start with the simple case we had before. So I just create my domain, the number of elements, and just use the linspace just to create the normal element. And now what we want to do is just pick an order, in this case 3. We can change it, but I stick with 3, meaning cubic. So now we want to add some higher order nodes. So if we have order 3, we will have order -1, so 2 additional nodes in between each one of them. And here the code may look complicated, so again I'm looping over all element. I'm creating the number of nodes, these lines here. So I'm creating this linspace, and the number of nodes will be like order +1. So for example, for a line we need 2 nodes, so order 1. For a parabola we need 3 nodes, 2 plus 1, etc. And since the first here and last node are already present in the linear space, I'm just excluding them from the arrays. And then at the very end, just appending the nodes, these higher order nodes. So again, first I'm creating the linear nodes, and then for every element I'm appending order -1. So if we go cubic, 2 additional nodes at the end of the list in the order from the first element to the last. So as before, we can try to plot and see what's happening. And here we will have the nodes and the other nodes in different color. So the linear nodes, we had them as before in blue here. And in between every linear node, while there is 1 orange, no, in this case, sorry, 2 orange nodes for the higher order. If we'll be picking order 2, so parabola, so piecewise quadratic, we'll have only 1 orange node. So this is not a big deal. So this is just important to remember that we just append them at the very end in order. So this is where, if you want to go to D or 3D, becomes messy and a lot of bookkeeping. So you need to be careful of where your nodes are and how they are associated. Another important aspect, which is not visible at all here because we're in 1D, is that this higher order node in 2D, for example, if they're on the edges of triangle, they would be shared by 2 different elements. So you need to be sure it's the same index. In 1D, there is only nodes in between elements, so there is nothing shared. Only the linear nodes are shared. In 3D, you may also have higher order node share across faces. So now that we have our nodes, what we can do is go back to the basic idea that we want to define some local basis on the reference element, and the reference element is always our segment 0, 1. And in this case, we'll not have only 2 non-zero bases, we'll have order +1. So in the very beginning of this tutorial, we had 2, 1 going up and 1 going down, because it was linear. If we have a quadratic function, we'll have 3, etc., etc. So, but again, as before, we only need to define them on the piece of this segment. We don't need to define them globally, which is really nice because we can hard code them. The important part here to remember is again related to the order, so we need to keep track of what we are doing with the indices. So as always, we were having the first 2 bases which were corresponding to the endpoint of our segment. So we want the base which correspond to the first and last endpoint to be the first and second, and then in order from left to right all the other higher order bases. So we need to be careful about respecting that order because it will be important for the local to global map. Again, this is really tedious bookkeeping, but it's not rocket science. It's something that's doable, just need to be careful with indices. So we had the basis functions, so we can define them as before. So we had these were our linear function, then the quadratic function. And again, here I don't want to go into the formula. You can verify that this, for example, this function here is the one that is 1 at 0 and 0 everywhere else. This is the function that is 1 at 1, and this is the function that is 1 in the middle. Again, it's important to respect the order, but you can really think about hard-coded, draw it on a piece of paper and to be sure. So these were the quadratic bases, and here I have a snippet of code for the cubic bases. This is again not super interesting. Just need to figure it out once, and then that's it forever. And since here we want to have this arbitrary order, I also create this utility function that takes the order and returns me the list of bases in the correct order. So I'm just calling the order the previous functions here. So now that we have the basis, what we can do is, as before, we can try to plot them. So now if we're going for cubic, we should have 4 bases instead of 2 as we were doing linear. So what I'm just doing here is sampling the reference element 0, 1, and then just for every base evaluate it and plot it. And this is how our 4 cubic bases will look like. And again, I just want to stress again about the order of these bases. So the first one is the one that is 1 at 0, and then 0 and 1/3, 0 at 2/3, and 0 at 1. The second one is the one that is 1 at 0 and 0 everywhere else, and so on. Then we have the one which is 1 at 1/3 here, and 0 everywhere else, and so on. So it's 1 and 1/3 here, and 0 everywhere else, and so on. So you see all these bases are in a certain order, and this again I want to insist is important. And on top of every node, which is 1 here, 0, 1/3, 2/3, and 0, there is only one which is 1, and all other are 0, exactly as what we had before. It just look a bit fancier. So before we are coding the gradient by just -1 and 1, here it becomes a little bit more complicated. It can be done by hand, but you can be stupid and just use SymPy to just differentiate this function. This is not a super complicated code. Just use SymPy to differentiate this head function we defined before and just put them in a list so we can get them. So we can, for example, plot the gradient. This is not super exciting. They look really, really weird. There is nothing interesting to see here, but at least we can verify if the gradient look correct and they look nice. So now we can construct the basis with the code with exactly the same code we had before. So the only major difference is how we want to do the local to global mapping. So before we had only 2 nodes, and the first node was E and the other one was E plus 1. Now, since we are doing higher order element, for the other higher order element, what we want to do is take the total number of elements, multiply by E, and add 1. So this again looks extremely complicated, but it's not. For example, the first higher order node of the first element will just be the number of elements. So the number of element -1 will be the last linear element, and number of element will be the first higher order node. So again, if you're confused by that, just think carefully. It's not really complicated, but it's something extremely important to get right, because if you mess up the indices, everything is off. So this is one of the important bookkeeping part in doing Finitera. So now we can just redo exactly what we were doing before. So we have our number of bases, which is order +1, not anymore 2. We just pick the bases exactly as we were doing before. The higher order nodes is just this function which I showed you before, and then I'm just appending from the linear node to the higher order nodes. And here I just want to say something extremely important in finite element. Even if you are using now cubic elements for the solution, doesn't mean that we need to use cubic elements for the geometric map. geometric mapping is completely decoupled from the choice of the finite element space. And this is extremely nice because we can have a linear geometry. Since our geometry was linear and is linear, there is no need of increasing the order, and we can just increase the order of the finite element space. We can also do the other way around. If we want to have a fancy geometry, for example, a curved geometry, we can just increase the geometric mapping and keep the finite element space low. And this is extremely nice because increasing the order of the geometric mapping doesn't increase the number of coefficients, the size of the linear system, etc. So the efficiency of solving on a higher order geometry is almost exactly as on the linear geometry. But in this case, we want to keep it simple. We just want to increase the order of the finite element space and not of the geometric mapping, so the geometric mapping stays nice and linear. But apart of this higher order node, the rest of the code is literally the same. So now we want to use the defined interpolating function as before. This is exactly the same code as before. The only difference here is that this loop, before it was hard-coded to be 2, now it's something else. We just get something higher order. It doesn't really matter. The code doesn't know that, and the code is literally the same. So now we can test it. So we just need to create this U, and now instead of creating U's only for the low order node, we're also creating some U for the higher order node. So you see here this is the first element, piece of the first element, and this is the second piece of the second element, and we got these two higher order nodes in between. So what's nice to see from this plot is that you see the junction where the element passes, they only see 0. The function is not smooth. This is not particularly important for finite element, but if you actually want to have a solution which is smooth, you cannot, even with higher order element. Everything will be smooth in between an element because we have this cubic function, but across there is nothing forcing it. So now we can assemble the stiffness matrix, and this is, again, I want to insist, is literally the same code as before. We're using QuadPy to integrate. We're just doing the loop over element, and here we're doing the loop over ij. See, exactly as before, now the I and j will range in something a little bit larger. But this line, which is the actual integral, doesn't change anything. Again, it's exactly the same as we had before. Now what we want to do is to set the boundary condition. So exactly as before, what you just want to set is that row to identity. And we want to set the right-hand side to 0 and some constant, exactly like we did before, 1 and 4 for the endpoint of our domain. And then we can just solve the linear system. Now the big difference here is that the matrix L will be a little bit less part. There will be more element in it, so the system will be a little bit more expensive to solve. But since we're in 1D, we don't really see it. So this is the price we are paying. We have more nodes, we have less sparse matrix, so everything becomes a little bit more costly. And now we can try to see our result, and again, the initial PDE was Laplacian of u equals 0, subject to this boundary condition, and now what we had before for the linear case was a line, and now the solution we know analytically should be a line independently from order, and this is exactly what we get. So we get some higher order nodes exactly as before. We get also some nice interpolating value in between, and all these values are nicely aligned, meaning what we are doing is consistent with the theory. So if the linear function is inside the space of finite element, we can retrieve it, and this is exactly what we get. So this is not really useful to use higher order in this case because the linear would also be fine. What if we want to do something more complicated, so move from Laplace to Poisson equation? So what we need is the mass matrix, and as for the stiffness matrix, the code is unchanged. It's exactly the same code we had before. And now we want to do exactly what we had before, so we want to set the right-hand side to 4, so we want to have a function which is 4, and set the two boundary condition to 0. So exactly the same code as before. We want to solve the linear system exactly as we were doing, and now when we plot it, instead of getting a solution which is piecewise linear, now we get a solution which is piecewise cubic. So even if it's not visible, the solution here across the nodes is not smooth. The transition is just a C0, but in this case it doesn't really look like because the solution is really nice. Okay, now just before finishing, I just want to go back to the very beginning of this tutorial and show you that the same code works even if we have a non-uniform mesh. So if we just create something random. So let me uncomment this part here. So now what we can do is create a random mesh and plot it, And now you see the blue dots are not uniformly spaced. The orange dots are still uniform between the dots because we want the spacing for the ordered nodes to be the same. So we can just define exactly as before the basis function, so I don't even need to re-execute this code because it's the same. The reference element doesn't change at all. We can use SymPy as before to compute the gradients, reconstruct the basis. Here the only big difference between the code from before and the now code is that the geometric mapping is not anymore constant, it's not the same for all elements, it will be different. We can use the same function to interpolate, and now if I execute this piece of code, we see there is non-uniform spacing between the nodes, but still everything is nice and interpolatory, and as before we get only a C0 transition between elements, like here. We can assemble the stiffness matrix, which is the same code as before, set the boundary condition, set the right-hand side, and solve the linear system, and at the very end we obtain a line again with non-uniform space, but again the line is there, so we should be able to reproduce the line. So again, we can complicate the problem with the mass matrix. We can set the right-hand side, solve the linear system, and plot the final result. And here, even if the nodes are not nicely equispaced, we see the solution looks really nice because the solution in this case is quadratic polynomial, and the quadratic polynomial is in the space of cubic functions, so the solution here is exact. Okay, thank you for listening, and that was it for the finite element introduction.
So, welcome to this part of our workshop, which covers the basics of geometry processing and visualization. And as before, in the previous tutorials, we have Jupyter notebooks available on our website, as well as a binder, so you can directly follow all the tutorial code that I'm going to present in the following in the Jupyter notebooks. For this tutorial, we need a few libraries. For the geometry processing, we need libgl. For the visualization of our results, we need meshplot. And for the So, welcome to this part of our workshop, which covers the basics of geometry processing and visualization. And as before, in the previous tutorials, we have Jupyter notebooks available on our website, as well as a binder, so you can directly follow all the tutorial code that I'm going to present in the following in the Jupyter notebooks. For this tutorial, we need a few libraries. For the geometry processing, we need libgl. For the visualization of our results, we need meshplot. And for the data representation, we use NumPy. And all these libraries can be installed with Conda or Anaconda. And it's just the command conda install, and then we install the libraries from the Conda Forge channel. So once the libraries are installed, we need to import them into our Jupyter kernel, and we can do this with the import statement from Python, and then we just import IGL, Meshplot, and NumPy, and that's all for our tutorial. Okay, so let's look into how we represent geometry with libIGL. So you probably are familiar with indexed face sets, and this is how libIGL represents geometry. So we have a vertex array that stores the position of our vertices of our surface, and we have a face index array that stores the connectivity and tells us which vertices make up which triangles. So for example, the first face indexes to the vertices 0, 1, and 2. So this makes up triangle 0, which is given in orange here. If we represent this in Python, this is directly done as NumPy arrays. So this example here, we would define the vertex array as a NumPy array, and then we just have 4 vertices, and each vertex has 3 coordinates, x, y, and z. So it's a 4 by 3 array. The face array itself is also NumPy array, and in this case we just have 2 faces, 2 triangles. So we have a 2 by 3 array, and each of the triangles has the first vertex index, the second vertex index, and the third vertex index in this dimension. So once we define the vertices and the triangles, we can directly plot them with Meshplot, and for this we call the plot function of Meshplot and just hand in the vertex array and the face index array f. Here I'm also setting the size of our viewer, so Meshplot opens this viewer here inside the Jupyter Notebook, and you can parameterize this, for example, setting the size of the output window. So now that we know how geometry is represented with libIGL as NumPy arrays, we can actually read in some geometry, and we do this with the libIGL function read triangle mesh. So this is a function that loads arbitrary triangle mesh formats, and if we're running this, we see that we actually get back 2 arrays, and these are exactly the arrays with the vertex array as well as the face array. So let's pick some names for those, and let's call them B and F again, and we're good to do some calculation on these arrays. So let's first maybe look at the shapes. So we see that we actually have 3,485 vertices, and we have 6,000 or roughly 7,000 faces in our bunny object. So next, we want to check that this is actually a bunny that we loaded here. So let's just call the Meshplot function and hand in the vertices as well as the faces. And we see this viewer opens again, and we can look at our geometry. Now if you want to write out geometry, let's say we have modified it, or we want to save it in a different file format, we can actually do this with the libIGL as well. So we just call igl.write triangle mesh, and now we can say, let's store this as bunny new.obj, and now I've forgotten to for sure hand in the geometry, so the next parameters are then the vertices as well as the faces. We could also pick a different format here, so we could also save as an off file, and the return parameter down here tells us that the file was actually saved. So let's go on. We learned about how to visualize surfaces, but what about point clouds? If we visualize surfaces, we can directly move to visualize point clouds by just removing the faces. And now you have a visualization of this point cloud. What if we want to also add colors, for example? So let's add the faces again, and now some color map. So for the colors we could, for example, pick the first coordinate of our vertex array. So let's just pick the x coordinate. And now we see that the bunny is actually visualized with a function on top of it, and the function is mapped into a color with a default NumPy matplotlib color map. We can do the same for sure also for point clouds, so we can also visualize the points with colors for all different types of visualizations and debugging. Okay, so we just learned about advanced visualization techniques. So in many applications we want to visualize scalar and vector fields. Let's say, for example, we want to visualize the surface normals of some geometry, and for this libIGL also brings a function, so we can just call the per face normals function of libIGL and then hand in the vertex and face array again, and here's some zeros for undefined normals, and then we get back the face normals, so one normal per face of our geometry. And to visualize these face normals we can, for example, pick color coding, so we hand in the colors again and we just use the absolute value of these face normals. Let's see how this works out. So this is the plot, and we see that the normal direction of our face normals is directly mapped into red, green and blue color values. So the colors show us into which the triangles point. For this we also set some shading parameters in order to avoid misleading reflections. So what if we want to visualize some vector fields? We can also use the normals example here, but in this case we use vertex normal, so we calculate one normal per vertex of our geometry, and libIGL also has this function available here. And now we visualize the vertex normals also color coded in this visualization. Let's do this first. So here we have a point visualization, and the colors of the points are representative of the normals in these vertices or points, and we can also add a vector visualization by just calling add lines function on our plot object, and we hand in the starting positions, which are just our points, and the ending positions of the vectors or lines we want to plot are just the points plus a little bit of into the direction of our vertex normals. Let's see how this looks. So if we visualize this again, we see that we not only have the points visualized now, but also the normal directions as vectors or lines. So what about not only visualizing normals, but also the curvature values? For this, libIGL also brings a lot of functionality with it, so we can calculate the principal curvature values, which tells us how much the geometry is curved in one point, and we can calculate this with the IGL principal curvature function, hand in VNF again, and now we get back principal curvature directions as well as the principal curvature values. So the directions are first, and we get two directions, D1, D2, and we get two principal curvature values, K1 and K2. This is the min and the max principal curvature. Okay. From this we can calculate the mean curvature. So the mean curvature is just the arithmetic mean of the principal curvatures, which means we just take 0.5 times K1 plus K2, and we have these mean curvature values, which basically tells us how much curved the geometry is at each vertex. Let me quickly move this down here to not confuse you too much. So we calculate the mean curvature and we use this as color coding. Let's see how this looks. So now we have the mean curvature value per vertex, and we show this as color values here as well. We can maybe also just print the mean curvature so that you get an impression what these values are. So these are values between 5 or -17 or even something smaller and up to 120, and Meshplot automatically normalizes these values here for the color mapping. So what if we not only want to use a color-coded visualization but also something different, like visualizing the principal curvature directions. For this we can use these add lines functions again, and we just add lines that go from the vertex position a little bit into the first or max curvature, principal curvature direction, and a little bit minus the direction of the maximum curvature, as well as yellow lines for the same for the min principal curvature. Let's see how this looks. So now we add this nice lines at each vertex, or crosses at each vertex, and they visualize the principal curvature directions everywhere on our surface mesh. So now that you have learned about how to basically load geometry and visualize it, you might also want to save the visualized results into a file, and this is also possible with Meshplot. So here we still have, in P, we still have the last plot. If you remember, this was just this bunny here with the principal curvatures visualized, and now we can just call the save function on this plot and give it a file name, and in this case we're just saving it as test1.html, and this code here lets me load this HTML file again into the Jupyter Notebook, and we see the output is that we saved the plot to test1.html, and when we're loading it we're getting the same plot. So we have this interactive viewer still, and we have the lines on top of our color-coded curvature visualization. So Meshplot gives you also the option to directly switch to offline plotting. So let's read another triangle mesh here, and then we're switching Meshplot to offline plotting. So this means that no plotting window is opened here, and then we can just set a file name to the plot directly, and the output is not a plotting window anymore, but a file saved to an HTML file. And this can be sent to somebody else, and it can be opened with a normal browser to have an interactive plot as this one here. Besides the visualization of geometry, it might also be interesting to get some statistics about your geometry or meshes, and this can also be done with libIGL. So if we read, for example, the bunny model again, we can then look into how many vertices are regular and how many irregular. We can, for example, find out the area of our faces by calling the function double area, but we can also get statistics about the internal angles of all the triangles, and by calling all these functions we see that the bunny, for example, has an amount of roughly 60% of irregular vertices, and we have, for example, the largest angle in triangles is 170 degrees, the smallest angle is 2.7 degrees, and the average angle is 60 degrees. So with these statistics you get some information on the quality of your meshes. In this tutorial we learn about some more advanced topics of geometry processing. We get to know functionality to do this and about possible applications. Again, we use the library libigl, which brings a lot of functionality for geometry processing, and most of it is already available in Python, so just a few lines of Python code bring you a lot of powerful tools with it. I just go through some of the applications that we learn about today, and these are, for example, parameterization for texture mapping, like here in this bubble. Then we will see shape deformation, as can be seen here. Another example for shape deformation with as rigid as possible energies. Then we will see smoothing of geometry, as can be seen here. We will also see how to calculate ambient occlusion and visualize it. We will learn about subdivision surfaces, eigendecomposition, and many more. More examples like this are also available in the libigl tutorials. So if you're interested in more, check out the libigl tutorials on the libigl website. So let's dive right into one of the first examples. So this is about parameterization of a 3D embedded geometry onto a 2D plane. And this can be used, for example, for texture mapping. And in this example here, we used a technique that is called harmonic parameterization. This harmonic parameterization maps our 3D geometry onto a disk. So the vertices that make up the boundary of the geometry, they are mapped to a circle, and then all vertices in between are mapped onto the area inside of the circle. So let's load some suitable geometry for this. So in this case, the camel head model. And as we can see here already, this has an open boundary, and this boundary we will now map onto. Or in the first step, we map this boundary onto the circle, and all vertices in between will be mapped to the area inside of the circle. So let's first compute this boundary. libigl brings some functionality for this, which is called boundary loop. So we just call boundary loop on our faces, and we get back our indices of the boundary vertices. If we call this, we have the indices in this BND variable, and we can now add points to visualize and see if these are actually the right boundary vertices here. And as these are indices here, we just use them to index into our vertex coordinate array and add those as points. And if we do this, we see that we just selected all points on the boundary. So once we have selected these points, we need to map these points or vertices onto a circle. For this, we can call the function igl map vertices to circle, and we just hand in the boundary vertices as well as the vertex coordinates. And now we get back the positions of these vertices on circles. So I just used the wrong order of the parameters. It should be like this. And here is something already still missing. Okay, so now we mapped all the boundary vertices that can be seen here to a nice circle. Once this is done, we can use these coordinates of this circle, of the vertices on the circle, as input to our next function, and these are the boundary positions for calculating these harmonic weight functions. So we calculate two harmonic weight functions for u and for v, and these can be then used as uv parameters for our vertices of the original mesh. So let's use libigl again, and the function is called harmonic weights, and now we just hand in the vertex coordinates, the face coordinates our boundary vertex indices as well as the boundary coordinates, which are the mapped vertex positions onto the circle, and we want to just have a harmonic mapping, so we just put in 1 here. 2 would be biharmonic. And what we get back here are the actual UV coordinates of all points or vertices in our mesh. Let's run this code and we get back this UV map, which we can now plot inside of the circle, and we see that a checkerboard texture is directly overlain on top of this, and we also see the wireframe of this original mesh. So this mapping has some problems, some distortion in these interior areas here. So there are better mappings that we see later, but this is a first start, and it's just that few lines of code to do this, to calculate this UV map. Now that we calculated the UV map, we can actually apply the texture also to our 3D embedded geometry by just adding the UV parameter map inside the plot call here again. And we see that our checkerboard texture is now mapped onto our geometry with the calculated UV map. The fixed boundary mapping approach from harmonic parameterization has some distortions inside of the UV map. This is problematic for some applications, so there are other techniques that try to minimize these distortions as much as possible. One of these techniques is, for example, least square conformal maps, or short LSCM, and this technique tries to minimize the conformal or angular distortions of such a UV map. Further details of the technique can be found in the libIGL tutorials, or also in the original publication that is linked in the tutorials. So the basic idea is that we don't have a fixed boundary in this approach, but instead let the boundary move freely in order to have these degrees of freedom to minimize the distortions. So instead of fixing the full boundary, we just need to fix 2 vertices, and in this case we fix vertices on opposite sides of the boundary, which are, for example, vertex 0 and a vertex in the middle of our boundary area. For these 2 vertices we choose 2 fixed positions, which are the position 0, 0, as well as the position 1, 0. Once we fix these boundary conditions, we can call the function LSCM. We hand in the vertex coordinates, the faces, the boundary indices, as well as the boundary conditions or boundary coordinates. After calling the function, we get back our UV map, which we can visualize as we've seen before. So here we have our UV parameter domain, and we see that the boundary is not a circle as before, but a free boundary that is formed in a way to minimize the distortions in the full mapping. And here we can also see the map or the texture mapped onto our geometry with the LSCM UV map. In order to compare this to the technique of harmonic parameterization, we can plot the 2 results next to each other. So this first result is the one with LSCM texture mapping, and this one with harmonic parameterization texture mapping, and it's not extremely visible, but in some areas you can see that the angular distortion is actually lower in the LSCM conformal mapping. Another approach for texture mapping is as rigid as possible parameterization, and this technique we will also later see for shape deformation. So it's quite a general technique, and we can use this for mapping a texture onto an object. So AREP tries to deform areas locally in a way that they are rigidly transformed, so that they are only rotated as well as translated. Further details can also be found in the original publication or in the libIGL tutorial. So for AREP we just call the this constructor here, we hand in the vertex coordinates, the faces, the dimension for which we want to run the AREP energy minimization, as well as the boundary or an index of the boundary vertices, which are set to fixed positions. Once we generated this AREP object, we can call the solve function on the top of this AREP object with arbitrary positions for our fixed vertices, and in this case we just set vertex 0 as a fixed vertex, and we set this to the coordinates 0, 0. In addition to this fixed boundary vertices, we also need to hand in an initial guess for all other vertices, and for this we just use the UV map that we calculated with harmonic parameterization. Again, we get back another UV map, which is the one we calculated in a way that it's as rigid as possible from our original mesh. And we see that this map is also a free boundary UV map, but the map itself looks quite different, and we see that the vertices are spread much more evenly inside the UV domain. Also, the result on top of our geometry looks quite different. We see that the checkboard is more evenly distributed over the shape. This is due to the fact that AREP tries to minimize the distortion in distances. So let's see this next to harmonic parameterization again, and compared to this approach, the result is quite different. The next topic we cover is shape filtering, and for this we look at two different smoothing techniques. So we input geometry into these methods, and the geometry comes out in a way that high frequency details are removed, and low frequency details or low frequency information is still in the mesh. These are two interactive examples, so we're gonna see the mesh smoothing as well, and we also make use of SciPy, especially the sparse solve function there to solve sparse linear systems. So first we read a triangle mesh, in this case the cow model, and then we build 10 different smooth versions of our geometry. Let's quickly execute to give you an impression, and then we're gonna talk through the code. So this is the cow model without smoothing applied, and now we can just animate through the different smoothing levels. Okay, so this is Laplacian smoothing. So what we do is we build the Laplacian with cotangent weights from our vertices and faces by calling the libigel cot matrix function, and then we loop over a range of 10 in order to build the 10 different smooth levels. So for solving or for doing the smoothing, we actually need to solve a sparse linear system, and we do this by calling spsolve, and then on the left hand side of our system we just subtract from a so-called mass matrix a little bit of our Laplacian matrix, a small delta of our Laplacian matrix, and on the right hand side we solve for the mass matrix multiplied with our vertex array. So the mass matrix is actually used to accommodate for the areas around each of the vertices. Since some triangles might be smaller or larger, this mass matrix tells us where to smooth more or less. And once we've calculated the smooth vertex positions, we just append them to this VS list, and these are the 10 different smooth levels. For the plotting, we do the following: just call our plot function and get our plot object back, and then we define a function with this interaction property here as a decorator, and we update the plot by setting the vertices of the according level that is chosen with this slider. Another smoothing technique is related to Laplacian smoothing, but still a little bit different and produces also different results. So this is spectral smoothing, where we make use of eigendecomposition of our Laplacian matrix. So let's first execute the code again. It takes a little while to calculate the eigen decomposition, and the smoothing we can see here on the right hand side again. So this is level 10. We can go down to level 2 and also up to level 200, and we see that the smoothing is a little bit different to what we've seen before. It produces different results. So what we need here is another geometry object again, the cow. Then we build the Laplacian matrix again, and we do an eigendecomposition of this Laplacian matrix, where we retrieve the 200 smallest eigenvalues and the respective eigenvectors. Once we got these 200 eigenvectors and value pairs, we calculate the vertex positions of the smoothed version just by taking our original vertex array, multiplying the transposed eigenvector matrix with these 200 eigenvectors onto this. So we transform our vertices into the eigenspace of 200 dimensions, and afterwards we transform back to our geometric space, and we get back smooth geometry. So, and the level here determines how many eigenvectors we use for transforming into the eigenbasis and transforming back from the eigenbasis. And each eigenvector can be seen as a frequency representation with a certain frequency, and the lower we go with our level, the less frequencies we have in our eigenbasis. So if we use more eigenvectors in the basis, we get a better approximation. If we use less, we get a smoother mesh with respect to this basis. So the next topic we cover is shape deformation, and here we look at two different techniques. The first one we already have seen in parameterization as well, and in this case we use a biharmonic functionality. So our next topic in geometry processing is shape deformation, and here we cover two different techniques. The first one is biharmonic deformation, and this is something that we've already seen in texture mapping or parameterization. There we've seen the technique of harmonic parameterization, and this is related here. So let's first show the animation, and then we're gonna go through the code line by line. So this is the mesh we loaded here that has 4 different regions. We have these green vertices, the yellow vertices that are allowed to move freely, and then the violet and blue vertices that are moved by a movement function that we define. When we go through the deformation step by step, we see that the violet and blue vertices are moving, the green vertices, they are fixed, and the yellow vertices in between their positions are calculated by this biharmonic deformation. And we see that the deformation is quite smooth. So let's go through the code line by line. We first load our triangle mesh, and then we swap some axes to have this rotated already. We then load the selection here. So this is a DMAT file, and we load these selections to have these different regions selected. in the next part of the code, we generate the movement for the vertices. So the green vertices, they are supposed to stay fixed at their position. The violet vertices are supposed to move forward, and the blue vertices, they are supposed to move downwards. And this movement description is written here in this UBC array. We then plot our triangle mesh, and the interesting part comes then here in this update function, where we actually calculate the deformation and apply the deformation to our viewer. So this deformation is calculated as a smooth deformation field, and this deformation field is calculated here. So we take our goal positions of the violet and blue vertices as well as the green vertices, but they stay at their original position, and then we take the original position of the vertices and we scale this by our step size. These are the boundary conditions then that we put into the harmonic weights function here, and the boundary indices are given by the selection here as well. And for the degree of the harmonic weight functions, we choose the degree 2, as this is by harmonic deformation. Choosing degree 1 doesn't change much though in this animation. Once we calculated this smooth deformation field, which we get back here from the function harmonic weights as d, we can update our vertices by just adding the deformation information on top of our vertex positions. And this deformation then moves not only the blue and violet vertices, but also the yellow vertices in a way that is smooth. Let's quickly switch to harmonic deformation here, and we see that it doesn't make a huge difference to the harmonic deformation. Maybe here at the nose it's a little bit visible that it's not as smooth as the biharmonic case. So the next approach for shape deformation is as rigid as possible shape deformation. And again, let's first run the animation. So here we have this night model with 3 different selected regions. We have selected the 2 feet as well as the head, which are colored blue here. And these regions are also fixed by our animation system, and the yellow vertices, they are allowed to move freely. So let's run the animation, and we see that the right foot of the knight is moving upwards, the head is moving sidewards, and all yellow vertices are smoothly calculated or interpolated in between. So what is going on here? We first load again our triangle mesh as well as the selection, then we gain our boundary indices from the selection, and we again generate this AREP object as we've done in texture mapping, but now we do this AREP computation in 3 dimensions. So the energy minimization considers 3 dimensions. We then also hand in the boundary indices, and we set the color here for the plotting to have blue colors here for the selected regions and yellow color for the free floating regions. So the interesting part then comes again here. We have the boundary conditions to define, and here we define for the left foot to stay fixed at its position, the right foot to move upwards and downwards again, and the head to move sidewards. And this is the animation code here, where we're scaling just some scalar values by this t parameter that comes from our slider. So with these boundary conditions, we then call the AREP solve function, which minimizes the energy so that the deformation of our yellow vertices are locally rigid or as rigid as possible. And this gives us the nice results where we can see that locally regions are not deformed much. It just does this global transformation to match the boundary constraints. To conclude this tutorial on geometry processing and visualization, I want to quickly go through a few further examples. All of these examples are also available in Jupyter Notebooks as well as in the libIGL tutorials, and you can go through them more thoroughly. So the first example is about eigendecomposition, and we've seen this before. So the basic idea is to calculate the eigendecomposition or eigenvectors and eigenvalues of a cotangent Laplacian matrix and then visualize those. We've seen this before in mesh smoothing, and here we just visualize the eigenvectors to get a feeling on how they work. So again, we use SciPy to calculate the eigenvectors here, and we just calculate the 10 eigenvectors to the 10th smallest eigenvalues, and then we visualize those on top of our geometry with a color coding, and we can now switch through the different eigenvectors and we see that they represent the geometry differently. The next example is about distances on top of our embedded geometry or geodesics, and here we have a function called exact geodesic which calculates the exact distances from one vertex of our geometry to all other vertices of the geometry. So let's execute this code and then we directly see what happens. So here we have our origin vertex, and now we get distances to all other vertices of our geometry by calling this function. And we color code these distances by parameterizing this periodic function here with the distance to the according vertex, and we see that this works quite well to give all the distances to all other vertices. Another example is ambient occlusion, and this tells us about how exposed vertices of our geometry are. So for this, libIGL calls into the library Ambry for ray tracing, and how exposed the vertex is calculated by shooting rays at the vertices and counting the intersections. That's the basic idea of this. Let's see how it works. So if we call the function ambient occlusion here and we tell it to shoot 50 rays for all of the vertices, we get back values for all vertices that tell us how exposed these vertices are. So for example, in such cavities here, vertices are not as exposed as, for example, here or on top of the head. And this is visualized here by color coding again with a different color map. In this case, we just use the gray color map. The last example I want to show here are subdivision surfaces, which are a way to subdivide coarse geometry to have a finer mesh. So we start again with a triangle mesh, which in this case is a coarse mesh, and then we have different methods for this subdivision. One method is just upsampling, just splitting the triangles basically. Another method is loop subdivision, which is more sophisticated and brings smoother results. So let's execute this code, and we see we have this coarse geometry here, and now we can switch to the upsampled version where triangles are just split. We have more vertices and smaller faces, but the overall shape of the geometry doesn't change. Whereas for loop subdivision, we get a nice smoothing effect of our geometry.
Alright, so this concludes the first part of the tutorial. We now have time for taking questions on both the introduction to FEM and the introduction to geometric computing. Okay, so we have one first question. Does IGL have support for PTEX? Sebastian?
Sorry, what is PTEX? I don't know it actually. Do you mean LaTeX maybe, or is it a special type of LaTeX?
We are getting an answer on the chat.
Shape format.
So one thing that there is that inside, as part of a Jupyter notebook, you can write formulas in there and get them formatted with. PTEX. Okay, yes. So I know what I can take this one. So no, we currently do not have support for this in the viewer. This is what we have for now is just plain UV texturing. Any other question? Okay, yes, another question is, do you support volumetric analysis as well, tetraedric-based meshes? And the answer is yes, both on the mesh generation and simulation side. And this is going to be covered later on in the week. It's the slide set before the last. So it's going to be on Wednesday. And we are also going to discuss the theoretical aspect of it in the presentation after the break, and then there is going to be a practical part on Wednesday on how to use it. Okay, let's see. Let's wait a few more seconds to see if there are other questions. Okay, so do you have any trouble using primitive index instead of pointers to primitives? So, I mean, they both allow you to do the same thing. The big advantage of using indices instead of pointers is that you can print them easily on a terminal and you can make sense of them. The other big advantage of using indices instead of pointers is that it's much easier to check when you go out of bounds, because you know how, if you know the size of your vector, it's very easy to check if the indices are within the valid range. So both options are okay. The reason why we went for indices is just because they make debugging easier and it's easier to spot problems. They have a slight performance overhead because you need to do one more read to actually access the data, but this is usually not something that is particularly relevant, especially for prototyping.
I have another maybe technical comment. On top of this is that when you're using pointers and your underlying data structure gets resized automatically by the containers, your pointer may be invalidated, which makes it extremely difficult to handle.
Okay, we still have time for one more question before we transition to the next part. Okay, it doesn't seem to be the case. So if there are more questions, as usual, just post them in either the Discord chat or the YouTube chat, and we're going to answer them in the next break. So the course now continues. There is a small change with respect to what was in the schedule. So instead of taking a break and moving to a different YouTube link, we are going to start immediately, and we're going to take it in the same link. So if you are on this YouTube channel, just stay in there. In a minute or so, the new session will start. Okay, so I think that's it for us, and there is going to be another Q&A at the end of the next video. You can start the next video, please. In this video, we're going to introduce all the different components needed for realizing a robust black box analysis. But before we go there, let's take a step back and let's look at where simulations are used in the wild. So Mechanical simulations like this bar here, where it's fixed on one side and there is load put on the other side, it's very common in mechanical engineering to estimate where stresses accumulate and where potential breaking points of the parts will be. In the aerospace industry, simulation of fluids, in this case of air, are very important for testing how the design will perform before fabricating them and doing measurements on the actual parts. In this example, a simulation is used to simulate and predict what will happen during a car crash. So this is commonly done in the prototyping phases to decide how components should be arranged and how to potentially reinforce the car to make sure that when the shock happens, it is absorbed without propagating to where the people are sitting. A more complex scenario, this is a simulation of a heart that includes simulating the organ and how the fluids moves. This is a very complex simulation that is placing together deformable objects with fluids, and this kind of approaches is starting to be used in the medical field, again, for predictive purposes. In graphics, we are used to use simulation, for example, to simulate, in this case, how snow moves and when it interacts with other objects. Another application of snow simulation is for predicting possible disasters. Simulation has been around for a very long time, and initially was used to predict astronomical position, eclipses, and other astrological purposes. And actually, the first general purpose computer was actually designed and invented for solving, at this point, simple simulations. But how does it look now? So this is an example from a modern software, and in here we are trying to set up a reasonably simple simulation. So we have a block on the left, which is fixed, and we have another block on the right, which is free to move, and we have something else in between. So the block on the right is actually being pushed toward the fixed block, and so we expect this part in the middle to compress. And if you try to set up this simple scenario in an existing software, you are going to run into a lot of issues. These are some comments that some of the problems that we encounter while doing this. So things like, it's important to draw domains right next to each other, or the model should be solved using a specific option called auxiliary sweep with small parametric steps, or you need to be careful what is your step size. So all of these makes it very difficult for people that are not engineers and have studied this software to use them. So if you do everything right, you're going to get the result that you expect. If you don't, there are going to be problems. In this case, overlaps that are absolutely not physical, and it's something that you cannot use for prediction purposes. So how does it look like? So the current design pipeline that we would like to have is something where the user provides us a model and provide us a set of boundary conditions. In this case, someone is going to sit in the chair, and we want to know what's happening. And if the chair deforms too much or there is too much stress, we want to go back, take this result to change the original geometry, simulate again, and make sure that nothing goes wrong. And right now, this pipeline requires a lot of manual effort, and it has really been optimized to have a human in the loop, always fixing things whenever things goes wrong. And what we would like to do instead is to make this entire procedure completely automated, so that there can be an algorithm that takes the output of the simulation, computes derivatives, and is able to directly modify the design to address eventual issues. The problem with this is that if you want to have such a pipeline, everything has to be absolutely automatic and there should be no user in the loop. So in general, there has been a lot of research on how to model the geometry of shapes, both on the graphic side and on the CAD side. And the focus here is really on geometry appearance, but on the other hand, other important aspects such as is an object fabricable with a specific technology, or is it stable, or is it robust after fabrication, or maybe like, can I slightly modify it to reduce the cost or the weight? All of these are very hard criteria, and what we are trying to do is to have an automated pipeline that allows to use simulation to improve these aspects without having the user to worry about it. And we would like to work on real-world objects, things that look like this, where if you try existing pipelines, they might not even be able to open such a model. And what we would like to do instead is to do optimization and to design objects of this complexity. This problem of automation and robustness is becoming particularly relevant with the introduction of machine learning, where it's now common to process huge collection of models. And when you are in the millions of models, there is nothing that you can do manually to each one of them. It will be just too expensive. So it's important to have pipelines that can be used to batch process data. And this is a topic, for example, for trying to use a data-driven model for physics. This is a very hot topic for which many papers have been introduced in the last year. Connected to this is robotics, where we want to simulate paths of, in this case, a robotic arm to check that it is safe and it's satisfying its purpose. Other example are behavior optimization of material, where we want to use a single base material, but changing the geometry, we can get it to deform in a way that we prescribe. Or to design prostheses for a specific person, where we start from a medical image and then we design a prosthesis for that person, and then we simulate how it will behave. And unfortunately, we are very far from there. And as you saw in the commercial software before, there's a lot of manual work still. But so let's focus on one specific case study to try to understand why this is so difficult. And let's take tetrahedral meshing. So the task is, I give you a surface mesh, in this case a triangle mesh, and I give you tetrahedra, and I give you only the triangles, and what I want to get is a collection of tetrahedras inside this surface. And there are many softwares that can do this. One is Seagull, another one is TETGen, DelPSC, and many more. And when I try to use this software, one of the problems I always had is that my models were never good enough. They always had small imperfections, like a hole somewhere, or an intersection, or maybe like a triangle of bad quality. And so I had to go by hand and fix my models until this procedure could be performed. And this is an important procedure because most of the standard simulation methods actually rely on having a mesh, a volumetric mesh. So I wanted to know what happens if it's just me being unlucky and having bad models, or if bad models are common. So this is a collection extracted from Thingy10K of 10,000, it is the Thingy10K collection of 10,000 models in the wild, downloaded from a website that is a collection of scan model, CAD models, manually designed objects, and procedurally generated objects. So what happens if we try to tetralize these objects? And the result is that the success rate of this method is pretty low. And the reason why it's so low is because they assume that the input has to be clean. And this is really far from being something that can be used robustly in a pipeline like what I described before. Because there, if we need to have it work every time we're trying to take a gradient. So the only acceptable option here is to have a success rate of 100%. And 79% is still pretty far from there. So why is it so difficult? So there are many reasons, but the main one is that the existing problem state that for many of the steps in a simulation pipeline impose strong assumption on what the input should be, and they just refuse to process data that doesn't satisfy these requirements. And while this is in general okay if you want to do things by hand, if you try to automate things, the code needs to be, and the algorithm needs to be robust to small imperfections in the input. In practice, most of the real data actually has problems. Also, the way models were modeled using traditional tools, for example, using trimming nerves, they do by construction, introduce a lot of the generic configuration. I mean, a model made of NURBS, usually it's not closed, and it has self-intersections by construction. And so it's impossible to expect it to be clean. And it's important to have algorithms that can deal with these issues. Also, implementing algorithms that use floating point, it's very hard because there are a lot of corner cases. And so if an algorithm is proved to be correct in arbitrary precision, for example, Delaunay tetralateralization, it's still very hard to implement it in floating point. And here you really have two choices. You can either do it right, and this increases complexity of the algorithm, or you ignore it. And in any case, getting something that works reliably, it's a very, very hard task. In particular, when many of these methods were introduced, large collection of data were not available. And so it was just not possible to test these on large scale. So what are the challenges here? So a big one, in addition to the one that I just listed, is that this is a specific case for a black box pipeline, is that in a typical current way of thinking about simulation, there are two separate stages. The first one is meshing. You take geometry in some format and you convert it to a mesh, which is usually a mesh of triangles or quads or tetrahedral cubes. And this mesh needs to satisfy a lot of requirements to be good. And then there is a second step, which is the actual solve time, where you build bases on these elements and you solve your partial differential equation. And these two steps are usually completely disjoint, where there is a set of criteria that the meshing needs to satisfy, there is a set of criteria that VFE discretization expects, and the two communities very rarely talk with each other. So what we argue here is that instead, this is the same problem. There is no point in generating a mesh if you cannot use it for simulation, and there is no point in doing simulation if you don't have a mesh before. And so what we are trying to do here is figuring out how to solve both of these challenges together at the same time. And we will see that doing this together dramatically simplifies both steps. So what our goals for this set of slides is to show you our efforts in going toward what we call a black box analysis pipeline. That means that we can automate all of these and do it robustly with minimal assumption on the input. So we want a method that is fully automatic. You should have no or minimal requirements on the input, and we're going to be more precise on this later. And we want it to be predictable. So we want it to have a predictable error in the simulation result in the end, or at least controllable. So the idea here is to sort of try to redo things from scratch, but now thinking that we want things to run automatically on large collections and integrate. So in particular, our current take on this is that for now, we are focusing on robustness instead of runtime. It's okay if things takes a long time to run, but we want them to be robust. And the reason for this is that they enable automation. So for example, if you want to prepare a data set for learning how elastic objects deform, you probably need to generate millions of simulation that you can use as samples for your learning algorithm. And you can run the million simulation in parallel on a big cluster. So it doesn't really matter what is the running time of one simulation, but what is important is that all the 1 million that you run are going to terminate, and they're going to produce a result that you can actually trust. And another comment is that having perfect geometry identical to what you provided in the beginning, it's not always something that you want. Finally, it's important to optimize at the same time meshing and finite element analysis. So what are we going to see in this set is, first of all, what kind of discretization do we want to use? So we need to partition our space in some way if we want to use a finite element method. So how do we do it? Do we want tetrahedra? Do we want cubes? Do we want splines? Do we want prisms or pyramids? So the first question is, which one of all these different options do we want and why? And in particular, the question is, since all the different finite element methods should produce the same result under refinement, the right question to ask here, in our opinion, is which discretization will give you the lower running time for a fixed accuracy, right? So that you can get the same result, a result of a given accuracy that will depend on the application that you have, spending as less time as possible. And it's less time as possible in the overall procedure, like including how long do you need to mesh, how long do you need to build your basis, how long do you need to solve. Then the second step is, after you know what kind of elements you want, can you robustly and automatically create such a mesh with minimal assumption on the input? So tolerating things like small gaps and intersection or degenerate elements. Then, after you have a mesh, a natural question to answer is, well, do I need to have a good mesh? And what does it mean for a mesh to be good? And is having a good mesh going to give me some advantages later on the simulation? And finally, after we know how to simulate, there are many other things to consider. One of them being, how do we handle collisions between objects? And how do we respond to contacts? So this is what we're going to cover in this video, but let me give you a very quick overview of all this, what's going to be the answer to these questions. So the first one is going to be a surprise answer, and is that for most applications, at least for elliptic and parabolic PDEs, it seems that tetrahedra are a very good compromise. They give you good performances, and we couldn't find any case where actually going for cubes will give you a noticeably major advantage. And tetrahedra also have a big advantage of being much easier to use. It's easier to create a mesh made of tetrahedra than one made of cube. And this gives us to a second point, which is, yes, we do have algorithms that allows us to create robustly tetrahedral meshes. Another surprise comes at the third point, where it's sort of well known that you want to have good elements, good quality. You don't want the tetrahedra to be completely squished, otherwise there are going to be problems in the simulation. But what was surprising is that actually what you can do instead of fixing the mesh is to fix the solver, to make sure that the solver is able to give you a good result even if there are elements of low quality. And then finally, it's actually possible to do simulation with contacts with minimal parameter tuning. And we're going to show a method for doing this and some results in this direction.
Let me move to the first part of the talk, in which I will explain to you how we discover, how to decide which discretization provides the best running time for a given accuracy. So this seems kind of a simple problem, and in fact there is an easy way to check that. So what we can do is just pick some elliptic PDE, something on the form of f, which depends on the variable x, the unknown function u, the gradient and the second derivative of u, and we want that to be subject to some boundary conditions, some Dirichlet on one side and some Neumann. So Neumann are usually used for something like a force. And this kind of PDE seems completely abstract, but there are some common, simple physical phenomena. One is elasticity, so how an elastic body deforms, and the other one is Poisson. Poisson is the classical cotangent Laplace, and it's used for diffusion process. So if we have this PDE, what we can do is just try to solve many PDEs on different meshes, on different domains, discretize both with TET and hexes, and try to discover which one is best, which one is faster with respect to a given error. So in the beginning I explained to you a little bit about finite element, and now we are not doing it in 1D, but we are going to do it in 2D and 3D, and for that we need to discretize our domain. So we discretized it before with a tiny segment, and now we need to discretize it with either triangle or tetrahedra. And as in my introductory on finite element, we also can choose the order of the element. So for example, we will decide and compare linear element, both tetrahedra and hexahedra, and quadratic, like well, in the tutorial we did cubic, but here we just stick with quadratic. There is no need to go so higher order. And also we will pick tetrahedra and hexahedra. And here I just want to set up some terminology. So for example, a quadratic hexahedron will be marked as Q2, Q for hexahedron and 2 for the quadratic. And for example, a linear tetrahedron will be marked as P1, so P for the tetrahedron and 1 for the linear. So before going into the comparison, I just want to give you a feeling on how this meshes looks like. So hex mesh, hexahedral mesh will look like nice regular grid in most of the part. This is something extremely difficult to create, but if the mesh if the meshing algorithm looks good, it's good. If the mesh will look good, the tetrahedral mesh will look more unstructured. But this is how the two meshes look like. So one of the simple experiments we can do is just try to see how these two method behaves for a regular grid where creating a hex mesh is trivial. So what we did, we just created a long bar, a cantilever bar. It's fixed on one side like in the picture, and then we will apply some vertical force on the opposite face. And what we can try to measure is the deformation at one of the endpoint of the bar. And here from this picture we see that, well, the linear tetrahedron in blue here, they perform really badly. The error is extremely high at the very end, something like 0.012, while linear also hexahedra are kind of okay, and at the very end the quadratic element, both tetrahedra and hexahedra, are performing similarly on the bottom, violet and red. But this is not really what we care about, so we now see that the error is kind of similar. What we really care about is the timings. So from this plot we can see that linear hexahedra are performing well, and from the initial slide, from my introduction, the linear hexahedra are only 8 vertices per element, while the quadratic tetrahedra are 10. So maybe there is an improvement. So what we can try to see is compare the time versus error, which is what we really care at the end. And here we see that the quadratic tetrahedra are better time versus error. So in fact what you want to be is on the bottom of this plot. The linear hexahedra are still okay, but not so good. And now before continuing, I just want to do a little parenthesis. Some of you may have heard about isogeometric analysis, and the main idea of isogeometric analysis is to use a spline as basis function for the finite element space. So I show you in the tutorial we can use this interpolatory Lagrange basis where there are 1 on top of one node and 0 everywhere else. Well, this is just a standard choice. One could also use something else, like for example a spline. The advantage of spline is that we will have a fixed number of degree of freedom per element. So even quadratic spline will have 1 node per element, more or less. The disadvantage is that since the spline have this extended smoothness, the sparsity of the matrix will be larger. And another big disadvantage of spline is extremely difficult to create a spline basis on a grid, on an irregular grid. So this works well for these banded bars, but it's really difficult to deploy in the wild. So let me show you the performance. So the performance on these perfect hex meshes for spline is also not great. It's similar to the quadratic tetrahedron. So from this simple experiment we can already see that while there is not much difference between Q and P for the quadratic, so not much difference between hexahedra and tetrahedra for quadratic element, but since tetrahedra are easier to create, at the very end it will be better. So this is not only true for this simple bar, it's also true for extremely near to be incompressible material. So if you know a little bit about physics, the moment something becomes incompressible, you have some things that goes to infinity in the PDEs. You have a concept which goes to infinity. So there is a common way, which is some kind of Lagrange multiplier like. So you introduce some pressure, and you can use something that's called mixed elements. So you have 2 discretization, one for the pressure and one for the displacement, and this kind of fix this problem of infinity. So here we see again the quadratic triangle in this case are really good. So these are the triangle, the quadratic triangle are really good, comparable with the mixed discretization, and the linear triangle are really bad. Solution looks something completely random. What's interesting to note here for the quads, the linear quads, the solution looks good. I mean, if you just look at the plot, you would say this is a correct solution, but in fact it's completely off and completely different from the real one. And again, the quadratic quads and mixed quad also have similar performance. So we also did experiment with nonlinear material model, and here we are showing the result for the 4 discretization. And again, apart from the linear tetrahedra, the other three are nearly indistinguishable. So one important difference here is the runtime. So the linear triangle are extremely fast. It takes more or less 10 seconds to solve. The quadratic tetrahedra also are around 1 minute, and the quadratic hexahedra are out of scale. So this is just a visual comparison. What we can do is we can look at the actual value. So here what I'm plotting is the deviation from a linear rotation in the angle across the section of the bar. So every bar here I'm sampling the displacement and computing the rotation angle and plotting the deviation from the rotation angle here. And we see again in this plot that the P1 as expected, so the linear tetrahedra are really not good. We see it also from the plot, while the other discretization are more or less overlapping. And here from this kind of plot we also that the orange one is not so good with respect to the other two. The other two are completely overlapped. What we can do to try to fix this problem is creating a denser mesh. So now they're really looking distinguishable. There is some still artifact on the linear tetrahedron, but the running time here goes completely out of scale. So the Q2 elements now take something like 31 hours, so more than 1 day. And if we plot the angle deviation, we see again the linear tetrahedron are not really good. They have all this jaggery, all the other lines are superposed. So these experiments are nice and good, but they're kind of just showing something anecdotal. So we should show some different material model, different discretization, but on a few experiments. So if you want to actually get some statistically relevant data, what we need to do is just come up with a large data set and try to test all this discretization with a different PD. So we just collected two data sets. The first one is the HexaLab. So HexaLab is a really nice project developed by some researcher in Italy, and it contains a collection of state-of-the-art hex meshes. So they collected something like 16 different state-of-the-art papers, and overall it contains something like almost 240 meshes. And let me comment on the flip later on. So this is the state-of-the-art data set. We also use MeshRAM, which is a commercial software which is able to create hexahedral meshes. And for the MeshRAM, we just downloaded 3200 meshes from the common Thinkit-NK dataset. So let me comment on the flips. So when you're solving a finite element simulation, what you need is all your elements to have positive volume. You can think about that if an element has negative volume, it will not be physical and the solution will not be, and the PD will not make any sense. So what's interesting to note is that all these methods, they guarantee to produce valid hex meshes, so positive volume hex meshes, but in fact they don't, so there is some problem in these methods. And let me add a final comment about this flipped element. If you ever try to do triangle meshing, there is this check of is the triangle flip or not, and this is exactly why it's coming from. So this is how we obtain our hex meshes, and well, we created for every hex mesh, we generate a tetrahedral mesh with that while, which will be presented later in this talk, with the same number of vertices. So now we have meshes which have similar number of vertices. So now with this large data set, we can actually compute and solve PD and see how the two methods are behaving. So let me start first with the HexaLab. So these are really state-of-the-art hex meshes, almost done by hand. And this is the result for the Laplace equation, and this is really difficult to distinguish, but I can draw some ellipses on top of it, and we see there is kind of a distinction between the linear and the quadratic element, but there is no clear distinction between the blue tone and the red tone. There is no really distinction between Q and H. So between P and Q, sorry. And this is the same exactly for the elasticity example. So here we have some linear and quadratic element. Again, they're kind of separated. The linear are performing less good, while the quadratic are performing better. But again, there is no clear distinction between violet and red dots. And again, these plots are just showing error versus time. So these are the perfect meshes. So even for perfect meshes, there is no much difference. And let me show you also the result for the large data set, for the Thinkit-NK data set. So this is the Laplace. Here there is no need of ellipses. We clearly see two separated clouds. On top, the linear one, which have They are faster, but they have higher error. Then on the bottom, there is the quadratic elements, which are slower but lower error. And again, we see the two clouds are completely overlapped. There is no clear distinction between violet and red, so there is no much advantage of hexahedral meshes. And more or less the same plot can be done for elasticity. Everything is kind of overlapped. And now, before concluding this part of the talk, I just want to again do a little parenthesis. So for Hex meshes, there has been some research in something that's called a serendipity element. So a serendipity element is an element which has something almost like a quadratic. It looks like a quadratic element, but it has a little bit less node to be a little bit more efficient. So if you think about a hexahedral element, have this tensor product structure, so at the very end your polynomial will be higher order. For example, a Q1 element will be linear on the 3 direction. Overall it will be trilinear and having this being this cubic polynomial. The serendipity element, they are kind of trying to reformulate the element to still be linear on the 3 direction but not contain this cubic polynomial in the middle. So you can create this serendipity element, for example, for instead of Q2. And this is showing exactly that. So you see they're a little bit faster here in yellow than Q2 because they have less degree of freedom, but they also introduce higher error. So even if you try to compare with this serendipity element, there is no much advantage with respect to P2. So let me summarize here a little bit. So we show here that P2, so the quadratic hexahedra, is superior or almost comparable to Q2. It's definitely superior to P1. So P1 is really bad. It has this weird artifact. So Q2 is better than Q1, of course, and Q1 is better than P1. So the bottom line here is that quadratic tetrahedral element are good, linear tetrahedral element are bad. And now I show you also some comparison with serendipity element. This was similar performance as quadratic element, a little bit worse error but a little bit faster. And then something I didn't show also because we have only preliminary result is the comparison with something we call pH, which is a polyhedral element. So when you create a hex mesh, it's really difficult to have cubes everywhere. So one question would be, can we leave some polyhedron now and there, and can we and what about the performance? So our preliminary experiment showed that this polyhedral element performed similarly to Q2, meaning at the very end that P2 is better also with respect to them. And then while we did this preliminary result with spline is slightly better for that simple experiment we have than P2. It's really difficult to compare them more in the wild because it's difficult to generate this basis for generic hex meshes, so this remains an open question. So this is the whole summary. So if you can use spline, well, it's probably a good idea, but in general it's really difficult, and since tetrahedral meshes are way easier to create, the best element here would be P2. So the result I show are just partial. If you're curious about this plot and you want to compare more dimensions, so I just show time versus error, the whole data is online, so there is this the results are on this URL, and we also have an interactive plot also linked from this URL where you can freely change the two axes to compare different dimensions and to see which elements is better. So before concluding, let me tell you a little bit about limitation about this study. So we kind of focus only on elliptic PDE, so we only show, for example, mechanics or Laplace and elasticity. We have no result for something like fluids. This is something we are working on now. Another important question is, what about time integration? Does it affect, do the different methods have different CFL conditions? Do they require different time stepping methods? This is still an open question. This is something we are working on now. I show you some example of this serendipity element, which is a common trick to try to make hexahedral element faster. It's still an open question. There are other trick also with respect to the quadrature, something called like reduced quadrature, hourglass control. This is something we haven't explored deeply. I just want to comment on that. If we start playing with the quadrature, the only thing we'll make faster is the assembly. And in all the simulation, in all our experiences, normally the solve time, which is dominating everything. So even if you make the assembly faster, the actual solve time will remain more or less the same, and you actually will damage the quality of the solution. And finally, for the large scale experiment, we only run with fabricated solution, which is kind of something artificial. This is not real experiment. So for fabricated solution, what we do, you start from a known function, and then you just plug inside the PDE to get the boundary condition on the right hand side. It's really difficult to come up with real physical experiment on thousands of nodes.
Now that we saw that a good choice for discretization is to use tetrahedral meshes, the next question is, can we generate them robustly without making assumptions on the input? And first, let's take a look at why meshing is so hard. So this is a CAD model that has been converted to a triangle mesh using an existing geometric kernel. And as you can see here, the triangulation looks very uneven. Now let's zoom in on that red circle, and you can see that there are a lot of local problems, a lot of set intersection, bad triangles, and these are problematic for certain meshes, especially if you try to decide what is inside and what is outside. Since there are self-intersection, it's very hard to tell. But let's look at another point. This also doesn't look great. And in particular, there is actually one region in the back. It's a connection between two patches. And if you zoom in there, you actually find that there are a lot of self-intersections there. While we don't know exactly where this model was coming from, it was part of a Fingit-NK, what it's likely that happened here is that the tolerance that is used to stitch together two patches that are close by was somehow different between the program that used to generate the mesh and to convert to a triangle mesh. Or something went wrong in the mesher. But it doesn't matter what the reason is, this is the input that we got. And while it looks fine from a distance, it's something that existing tetrahedralization methods don't want to process because, indeed, it's invalid. It does not contain, it does not encloses volume. On the other hand, we would like to be able to use it if that's what we have. So, but why is it so difficult to represent 3D geometry? And the main problem is that there are many different ways of doing it. You can use implicit function, you can use meshes, and you can use a manifold atlas. And even if you pick a representation like meshes, for the same surface, you can have many different kinds of meshes. So differently from images, there is not a clear way on how to represent surfaces. Another thing is that many of the operations that are usually done when you deal with 3D geometry are not closed under the representation that you use. A simple case is if you just are on a plane and you compute the intersection between two segments, the intersection point is not going to lie on any of the two segments if you use floating point, just because there is rounding happening. And so what do? I mean, you have to do operations and your representation, your points are in floating point. So how do you do it? And here you really have two choices. One is you ignore the fact that this happens and you just ignore the fact that the operation are going to introduce errors, and this will result in algorithms that are not robust, that people probably have parameters that you need to tune, and if they're wrong, the algorithm will break. The other option is that you do handle it, and if you do that, your algorithm is going to just become more complex, and the more complex it is, the more likely it is that you have bugs in there. So it's something that needs to be done carefully, and one way of doing it is to actually test your algorithm on large collection of data to make sure that at least on this large collection of data, everything is fine. And so this is what I showed you before. If you take these and you test existing tetrahedralization method on this input, this is what you're going to get. Some of this is due to input invalid, some of this is due to the fact that the algorithm crashed because there are problems in how operations are done inside, or maybe just implementation bugs in the algorithm. So what we propose, it's very different from what existing methods do. So instead of having our statement as, I give you a boundary and I want to fill the interior with tetrahedra, we're doing something different. We're going to give you some input that in this case is completely unstructured, it's just a collection of segments. I'm making an example in 2D just to make the explanation more clear. And then our goal will be to, initially we're going to build some envelope, you can think of it as a shell around the input segments. And then what we want is now to reconstruct a mesh that stays inside this envelope. So our idea is that instead of trying to exactly reproduce what we have as input, we want something that is close. And this definition of close is something that the user can control. So you can decide what kind of error are you willing to tolerate. And so now this at the first look might seem weird, like why would I want to destroy my geometry? This is my input, I want to be as accurate as possible. But the reason why you might want to do it is because, for example, if you have two things that are very, very close together, or a triangle that is almost degenerate, if you try to keep that degenerate triangle in your output, you're never going to be able to get a good mesh. On the other hand, if you think of it as a more in a application-driven way, where, for example, your object might be used later on for doing, I don't know, CNC milling, it's really pointless to represent in your geometry features that are much smaller than the tolerance of your machine. I mean, anyway, you will not be able to represent these when you generate instructions that you have to send to your machine. So the idea here now is that we are gonna do the operation that we want to do, in this case meshing, but up to a certain tolerance that is under the control of the user. So our new take on tetrahedral meshing is the following. We start from the input. We do a set of operations that are trying to simplify the mesh as much as possible to reduce the number of triangles while satisfying the geometric tolerance that we prescribed. Then we are going to generate a volumetric mesh just uniformly with a grid over the entire space. And then, one at a time, we are going to insert these triangles as faces inside the tetrahedral mesh. And this operation is an operation that, if you do in floating point, will fail, because there are going to be numerical problems. There are potentially tetrahedra that have zero area or even flipped. And so what we do instead is we postpone. Every time we cannot insert a triangle, we don't do it for now. Then we are going to do local operations to try to make the quality of the tetrahedral mesh better. And then after this is done, we're going to try to insert more triangles. So this procedure is guaranteed to stop at some point. I mean, we either insert all the triangles or we cannot insert some of the triangles. But in practice, we are always able to insert this triangle, except in extreme cases where you are trying to really insert sliver triangles that cannot be inserted due to floating point problems. So after this is done, we remove all the tetrahedra that are not inside the volume, and we keep the one inside. So this is the entire idea, and so the key part here is that the algorithm produces a box of completely filled with tetrahedra, and the tetrahedra have faces that are close to the input triangles. So this is what we do. And this final filtering to decide what is inside and what is outside is a heuristic step, but is not really needed for every application. It depends. It's something that it's down application dependent. I mean, of course, this filtering, it's easy if your mesh is clean, but in our case, the focus is to also being able to do it for meshes that are not clean. So if you do it in this way, our success rate is 100%. And what it's exciting is that despite the increased robustness, our method is in speed comparable to other implementations. It's actually faster than Seagull and slightly faster than Tetsu. And so in this way, you get robustness. You also have reasonable running time. What you pay is that you might have some errors, geometric errors with respect to the input. So this is something that on every application is going to be different. I think for most practical applications, especially the ones that are targeting simulation for then feeding back the object to the real world and fabricate them, it's very reasonable to have some tolerance that is comparable to the machining tolerance. Since anyway, you will not be able, when you fabricate the object, to have something that is more accurate than that. What you gain is that now you can provide to the mesher more or less whatever you like. You just need to provide the triangle soup. So this is an example of a mesh with many horrible triangles in the bottom and on the left, and that you see that is on the right, it gets cleaned up and you get a very nice tetrahedral mesh out of it. And if you only care about the surface mesh, you can also just take out the boundary of a tetrahedral mesh and use it as a surface mesh. This is the bridge, the part of a clock that I showed you before. And here you can see that the triangles gets cleaned up, And what you get in the end is a mesh that it's much coarser than what you had as input, and clean. Like all these nasty collection of set intersections are resolved. For this specific model, it takes a while. So as a rule of thumb, like models that have more problems takes longer to be meshed, but still, in 1 hour, fully automatically, without any user interaction, you get a clean model out of it. This is an example of what this technology allows you to do. This is an example on the left of a collection of cylinders. This is a pillar, and this model was generated by simply putting together all the cylinders without really caring about how they join together, and then our method was used to, at the same time, clean up all the self-intersections and give you a good tetrahedral mesh. And so here you can really go from a quick script that generates a geometry and then feed it to our method to get a mesh that can be directly used for simulation. The parameters that you really need to pick is the envelope, like the tolerance, the geometric tolerance that you allow it to deviate from the input. And here, the limitation of the algorithm is that the smaller is the geometric tolerance, the denser is going to be the output mesh, and the slower the algorithm is going to be. So especially for the small envelopes, this difference might make a big difference. A side effect, a positive side effect of our algorithm is that we can use this method not only to generate tetrahedral meshes, but also to clean existing meshes. So in this case, we have a mesh on the left. The one in the middle is an example of another software that is used to just clean up the surface. What you see on the right is an example where our method was used to create a tet mesh of the input, and then we throw away the tetrahedra and we only kept the surface. And what you see here is that the mesh is clean, it has good quality, and it can now be used in downstream tasks. So this procedure can also be used not only to generate tetrahedral meshes, but also to clean triangle meshes. You can use this to do Boolean operations. The idea here is that you can take as many meshes you like, you put them all together, you mesh the entire box that contains them, and then you decide which tetrahedra to keep using some rules that depends on your tree of operations that you want to perform. And this is a way, that this is a method that allows you to do Boolean operation while at the same time generating a mesh that is immediately usable in downstream applications. Well, the meshes can be used directly for simulation, as you're going to see later in this presentation. And in particular, this idea of being able to take meshes, do Boolean, and directly simulate allows you to very quickly have do complex simulations like this one here, where you have a tube, you have a complex object, you put them together, you mesh the space in between by doing a Boolean operation, a Boolean subtraction, and then the mesh is ready and can be directly fed to an FEM solver for, in this case, simulating a flow of liquid passing through the tube. So what are the limitations of this approach? Well, one limitation is that what we are really doing is mesh an entire box around the object. And then we need to decide which tetrahedra are inside and which one are outside. So if a mesh is clean, this is easy and there is nothing to discuss. But if it's not, then we need to somehow decide which one. And we have different strategies for doing this. One is the winding number, another one is float filling. But at that stage, if a mesh is not clean, we need to use some heuristic to decide what might be inside and what might not be. So while this heuristic works pretty well on average, it's possible to produce corner cases where the heuristics like drop some components or delete some part of the input that we expect to be there. Especially like if the input contains shells that don't actually enclose a volume, like open shells, then there is really no way we can know what is inside and what is outside. It's really undefined, and so the algorithm is going to keep or throw away parts that we might not expect. Before we move on to the next topic, I also would like to briefly cover curved meshing. So up to now, all the meshes we had always had straight edges, but this doesn't need to be. You can also use meshes that have curved boundaries, curved edges. So what does it mean? Well, you have in this case you have a triangle mesh, and some of the edges of this triangle mesh can be curved. So it can be polynomials of order higher than 1. And what you get by doing this is that you can approximate the same, you can represent the same geometry using a smaller number of elements. And it turns out that the cost of a simulation depends mostly on the number of elements. And actually going to curved meshes, it's a small cost. And so what you do here, what you can do if you have curved meshes is you can use a coarser mesh to still get the same quality. And so you get, in the end, faster simulations. But not only this. So the fact that you can use curved meshes means that you can actually reproduce existing curves exactly. For example, in this case, you have an SVG, and if the degree of the curves inside the SVG is limited, you can reproduce it exactly using quadratic or cubic curves. So you might actually get a mesh, which is a discretization of the space, which is exactly reproducing your boundary. And this will give you a more accurate simulation in the end. I mean, if you use piecewise linear elements to approximate something that is not piecewise linear, you're always going to have an error. The error is going to go down if you refine, but it's never going to be exactly zero. While with curved meshes, you have a chance of actually reducing it to zero. So we have a similar pipeline to what I presented before for dealing with curved 2D triangulation. So here the input is a set of input curves. We do an initial cleanup to make sure that the curves are not too close. If the curves are too close, like numerically close, it's impossible to have good quality. So we need to do some cleanup of the input to ensure that they are all separated by some tolerance. And then we can use a pipeline similar to the one that I presented for tetrahedral meshes to create a background mesh made of triangles. In this case, similar to before, we are meshing an entire box around our object. Then after this is done, we can improve the quality, and after the quality is improved, we can curve the elements to match the input curves. And here, the important part of this algorithm is that we need to create the linear mesh already thinking about the curving that is going to happen later. Otherwise, the curving might not be possible. Our idea for this algorithm is that we're going to try to do our best to curve without breaking the mesh. So we only curve if we don't make the geometric map having a negative Jacobian. So in this way, we can always guarantee to produce a valid mesh, but the downside is that we might lose some, do some small error in reproducing the input curves. So in practice, this argument works really well. We tested on a collection of SVGs, and you can see here that even for very complex geometries, we can get a mesh with these features in. These are examples of self-intersecting curves. And if you want to see more, we actually run these on a collection from OpenClipArt. We got 20,000 SVGs from there, and we just run it on all of them, and we got a valid mesh for all these cases. Success both in the tetrahedral meshing and in this case means that within a certain time it terminated creating a valid mesh with no inverted elements. What can you do with this? So you can, for example, do diffusion curves, which is a technique that is introduced by Adobe a few years ago. The idea being that you have a drawing and you have color assigned on the two sides of the curve, and then you diffuse it, solving an harmonic problem. And here, the advantage is that, as you can see here, flickering between the two, in this case, the two meshes have the same number of elements, so the cost is almost the same. The difference in runtime is around 2-3%, but you can see clearly that one result is much better than the other because you don't see the linear edges. So here you are essentially paying in a little bit more complex algorithm to create the mesh to get a result at runtime which is much better for a tiny performance overhead. So I think this is an exciting direction. Another example, this is a fluid simulation. You have this square filled with, like cut with small holes, with this array of holes, and you have a flow passing through. Here is what you get with a curved mesh. And now we are going to look at the same result with a linear mesh at the same resolution. So note how here all these lines are very nice, smooth, and symmetric. As soon as we switch to the linear mesh, you can immediately see that the symmetry is broken, the circle don't look like circle anymore, and the result that you get is clearly different. So again, if you can mesh with curved meshes, you get a better result for more or less the same cost. This is an example of elasticity, and here we are comparing a coarse curved mesh against a dense linear mesh. And what you can see here is that they are indistinguishable in this scenario. They are almost the same. The big thing is the difference in timing. There are like multiple order of magnitude of difference in what we have to do for the one on the right and what we have to do for the one in the middle. So there are many limitations in our implementation of this measure. So for now, we only support cubic Bezier in curves in 2D. We can only do isotropic meshing, and we cannot guarantee that all the features that you provide are going to be preserved. So there can be like small parts that are not preserved. Extending this method to 3D is highly non-trivial, and this is one of the things that we are, one of the big problems, big challenges that we are trying to solve.
We know we can generate tetrahedral meshes robustly. The big question is, do we need to create perfect meshes with perfectly regular elements, or can we run simulation even on imperfect meshes with some elements which are really bad? So this is what I will try to explain you in this part of the talk. So before going there, the big question is, does it really matter? Do we really need to have these perfect meshes, or can we run simulation, or the simulation is really not affected? So for doing that, I will just pick a super simple PDE, which is the Laplacian of u equal f, with f equal to alpha x squared. And for this simple PDE, the solution is just u equal to x to the 4, which is just this glorified parabola plotted here. So now if you want to solve this PDE with finite element, what we need to create a mesh. In this simple case, the domain is just unit square, so to create the mesh we can just create this beautifully regular mesh with all right angle triangles. So now we can run finite element and see how the solution looks like, and this is how the solution looks like. You may think that this is in fact a bad solution because it has these kinks a little bit everywhere, but in fact this is a really good solution, and the kinks comes from the fact that the mesh is really coarse. But I would say this solution looks similar to the other one and everything is fine here. So now if we want to observe or study the effect of the quality of the mesh on the solution, what we can do is there in the middle in this strip we can start putting more and more bad element. So this bad element will be a tiny long elongated triangle, and we had more and more strip of them, and you see as we are adding them there is something happening and appearing in the middle of this solution, and if I continue to add them you see start lifting, and the more we add, at the very end mesh doesn't look at all like the initial one. And I here want just to stress the fact that there is no numerical problem for solving this PDE. We're just using a linear system, and the linear system is solved with a direct solver, so there is no numerical error. And the size of the triangle there in the middle, even if they are not visible anymore in the close-up, they are still reasonably large to not create any numerical problem. So the bridge appearing here, or this completely weird artifact, is completely due to the fact that the quality of the mesh is bad. You can think about that this triangle here in the middle, they cannot bend over there, they're stiff and straight, so this is why it's creating the bridge. So one thing, if you are doing meshing, you can think, well, that's who cares, let's try to remesh this mesh. So in that previous case we can try to smooth and move stuff around. This is in fact an expensive process, but let's think about, can we always do it? And in fact for this kind of thin long feature we can, and in fact the remeshing will make everything even worse. So let me try to give you the feeling of why this remeshing cannot be applied for this kind of meshes. So you see that feature, this long elongated feature, creates problems. So let me show you in 1D. So this is the tiny elongated feature, so let's try to create one big triangle there. And you can think about that this triangle is kind of baddish because it has this acute corner. And if we try to refine it and to remesh it, you see what's happening in the acute corner will become more and more acute, and in the limit it will become a line. So remeshing here is really not an option. We are even making things worse. So how can you actually compensate for the bad quality of the element without doing remeshing? So our idea is to locally increase the order of the element to compensate. So I show you in the tutorial about finite element that we can have a linear or cubic element, and when we compare to tetrahedra and hexahedra, I show linear and quadratic element. And all the meshes there were all linear and all quadratic. What we can do is start mixing elements. So we can have linear element where the quality of the element is good, and we can have quartic or cubic element where the quality is bad. And you can see from this picture here that the good element, the one that look like a regular triangle, they are all yellow, remaining linear, and the bad one, like next to the neck of this frog-like animal, they start being quartic with really high degree, and in between there's some kind of quadratic and cubic element. And I just want to point out that this idea of increasing the order of an element is something that's in finite elements quite common, and it's something that's called a refinement. And in fact, there are two kinds of refinement. The more classical one, which is edge refinement, where the idea is to increase the resolution of the mesh locally. And this has been widely exploited in graphics, for example, for cloud simulation or cracks. And it's important to notice that this edge refinement is usually done a posteriori, in the sense that we first solve the PDE, have some heuristic to decide where there is too much error, and then refine the mesh. The other kind of refinement is still a posteriori, is something that's called peer refinement, which is more similar to what we are doing, and this is also something dating back the original finite element with Babushka, for example. And again, this is a posteriori, so you first solve the PDE and then have some heuristic and decide where to increase the order of the element to compensate for the bad solution. What we do instead is kind of similar but completely orthogonal, because what we do is a priori, we only increase the order based on the input, so we don't care about what is the solution, we only increase the order of the element to compensate for bad geometry, for bad input. We never solve twice. And I just want to point out that our technique can be completely combined with the other two, so you can solve with our method and then use some heuristic for a posteriori peer refinement, or use some heuristic to refine the mesh with edge refinement. So how actually we can decide where and how to refine a priori. So to do that, we have a simple formula that looks scary. So let me explain you this magic formula. So this magic formula, what it does, it relates the order k of an element. This is what we want to assign. And this relates to other quantities. For example, a user control parameter, a tolerance, this b, in all our experiments just used 3. So this is just giving us a little bit of tolerance. And then, while we have the average edge length of the mesh, this is something super simple to compute. We got the minimum order, so what is the usual order you want to solve? Usually it's 1, and then we have some constant which are related to the shape of a perfect element in 2D and 3D. So this is square root of 3 divided by 6, so square root of 6 divided by 12, this is just a constant. And then finally some local quantity related to the current element. So we got HE, which is the maximum edge length, and then we have sigma E, which is the ratio between the radius of the inscribed circle and the maximum edge length. So I just want to point out that all these quantities are really simple quantity to compute. They only depend on the local order. So again, if you give me a triangle or a tetrahedron, we can easily compute this sigma and h using some geometric quantity like the volume or the surface of an element. So give me an element and I can give you immediately k, and it's extremely easy. There is no complicated computation here to be done. Once we have k for every element, what we need to do is to assign it to every element of the mesh. And what we need to do is we need to iterate with a simple loop over the element and compute ke using the formula. So we need to just compute k for every element. And now the formula is telling us, well, we want that element to be degree 3 or degree 2. And the problem is, if our degree element, for example, degree 3 element will be next to a degree 1 element, well, you will lose some degree of freedom because of the element next to it. So what we need to do is just increase the order of the element e and every face or edge into the neighbor. So if you want the element e here to be p3 in pink, well, we need to increase the order of the 3 edge neighbors of e also to 3. So now e is full degree order 3. And if we do something like that, this is how our mesh looks like. So this is really simple. Just loop over the element, select the degree using the previous formula, and just use the navigation of the mesh to compute the degree. Now we have this mesh, we have some linear and cubic element next to each other, and one of the basic requirements in finite elements have a continuous basis, C0 basis, and now we end up having a linear and a cubic element, and of course will not match on the interface. So what can we do? So this is a simple example. We have a linear element in yellow and a cubic element in pink, and if we want them to be continuous, well, what we want is on the blue line here in the middle, we want the basis to be linear. So the linear basis will be linear, but the cubic will not. And the trick here behind that is we can think about a linear function as a special case of a cubic function with two special coefficients, 0 for the quadratic and the cubic term. So the only thing we need to do is to constrain the nodes of the cubic element, the one we have to match, to some constant to ensure that the basis is linear, and thus killing these higher order terms. And there is a really simple way. For example, if we just change this weight to 2/3 and 1/3 and add them as a contribution to the linear basis on the corner. And in fact, if we do that, we just obtain this nice basis, which is cubic on one side, as you see, and then it's nicely meeting the linear basis on the other side and being linear in the middle. So this is how you construct the C0 basis. This may seem a little bit technical. What you need to do is to change the local to global mapping. But I just want to stress out, if you have a finite element code that already supports a posteriori peer refinement, the only thing you need to do is just use the existing machinery with our formula. So this is something quite standard in finite element. So now that we have final C0 basis, the only thing you need to do is just set up and use this basis for your simulation. So let me go back to the initial example with the Laplace, and on one side I'm showing you the standard finite element, on the other side I'm showing our result. And well, in the beginning the mesh is good, so our method still doesn't do anything and keeps the element linear. The moment we start having bad and worse quality, well, you see some pink appearing and our method will automatically increase the order of the element. And here we kind of see the price to pay. To compensate for this bad quality, we have some higher order element, and it takes a little bit more time, something like 3 times more. And if we destroy the quality of the mesh even worse, well, the color of the element will become darker and darker pink. So here we have some cubic element. The solution still looks perfectly good, and here is the price we have to pay. It takes something like 10 times more to solve. This is not such a big deal, but it takes a little bit longer, but there is no parameter tuning. Everything here is completely automatic and the quality of the solution remains good. So this is of course true not only for the Laplace, it's also true for nonlinear equations. So on top I have 2D, and the bottom I have 2D. On one side I have the standard, so normal linear element. On the other side I have our solution, and we do the same experiment. We introduce more and more bad element, and you see how the solution looks like. So for ours it doesn't move much. For the standard element, the solution moves a lot, and at the very end it looks completely different from the initial one. So as for all our other work, we are not only satisfied on testing it on one model, on some model. What we did, we just took this Thingy10K dataset and generated 2 datasets. Since we want to study what is how our method is behaving for bad meshes, we run the tetrahedral mesh completely and fully optimized to the very end to get the best possible quality, and we also run it for the non-optimized. So we just stop the optimization as soon as possible. So before showing you the result on this large data set, there is a question how we actually measure the error. So this is the standard L2 estimate for finite elements. So this is just showing us the L2 norm of the error, and what it does is just compute this norm between the actual real solution and the approximated solution. And so the exact solution is what we had in the very beginning. This is how it looks like. This is our approximated solution, and the big problem here is that this estimate will have this h squared in it. So we'll have a different h for every model, since the model have different scale, different resolution. So if you just try to compare this error, it doesn't really it's not really similar. We'll have a different h for everyone. So what we come up with is a different measure to kind of remove that, something we call L2 efficiency. So we just take this L2 norm of the error and just dividing it by h squared. So this is kind of giving us the constant C, which is what we were targeting for. And just want to point out that here having small value is something good. So let me show you the result. So in green is our method, and in yellow is the P1, and you see that the efficiency for our method is low, meaning it's good for both fully optimized and non-optimized dataset. So our method automatically compensates for the bad quality of the element having really low efficiency, which is extremely good. Of course, the price we are paying here is we are sneaking in more higher order element. So for example, for the fully optimized dataset, since the meshes are good, we mostly have linear element with 73% P1, and of course the measure cannot always generate a perfect element. Sometimes it will just be impossible because elements next to the boundary are difficult to optimize, so there will be something like 1/4 of quadratic element. If we run our method on the non-optimized dataset, while we end up having way more quadratic element, less linear element, most of the elements are bad, so we need to compensate for the bad quality, and there are also cubic and quartic elements sneaking in. There are 10% of cubic element and 1% of quartic element, and this is exactly what we are paying the price. So we have more higher order element, and thus we have more a larger number of degree of freedom. So this is the ratio of the increase on degree of freedom. So for the fully optimized dataset, we have more or less twice the number of degree of freedom of non-standard finite element. For the not optimized, we have a much larger curve, and we have something like 6 times more degree of freedom than the standard finite element. So this will give us higher running time, but again, this is fully automatic, and you don't need to care about having good meshes. This will automatically compensate for the bad meshes. So I just want to show you some timings. So we see that our method is kind of a little bit slower, and for the non-optimized meshes it's even a little bit slower. But again, this is fully automatic, and there is nothing to be done. This is a small price to pay. I also want to notice that the optimization of the mesh is something complicated to do. So if we are slower in solve time, but in fact the meshing will be faster. So before concluding, let me give you some limitation, explain to you to conclude this work. So first, again, we study only elliptic and static PDEs. The analysis of the formula is more complicated for dynamic simulation and for non-elliptic PDE. Another thing, we just compensate for the bad quality. We have no actual control on the actual error, because the error at the very end depends also on the L2 norm of the solution, which we don't know. So we need to mix our method with some a posteriori p-refinement. And there is something to be said about having higher order element. It kind of degrades and makes the condition number of the system a little bit worse, which kind of influence the timing for linear iterative solver. This is not something we saw in our experiment. At the very end, the condition number was still limited, but it could affect the performance of the solver. In the last part of this tutorial, I want to explain to you how we can actually automatically simulate the collision between soft objects in a completely black box manner. So no parameter tuning, everything is perfect. So we started from deciding which discretization we want to use. Then we show how to actually generate mesh robustly. We show that we can actually compensate for bad quality. And finally, the big question is, can we upscale it to more complicated simulation? So this is based on a recent paper we just published at SIGGRAPH, and this is called incremental potential content, ICP. And the whole goal here is to run simulation robustly. So in the very beginning, we show you this state-of-the-art simulation software, and for this super simple simulation where we had just two squares colliding to each other, there were massive failure if you had the wrong parameter in. And this is true not only for state-of-the-art software, but it's also true for research parameter. So here this large table is showing on every column a different state-of-the-art method for solving contact problems, so collision problem. So here we have something like 6 of them, and every row here is a particular simulation we want to solve. So for example, in that corner there, what we are just trying to simulate is just a tetrahedron falling on a plane. Now you notice that every one of these entry of this matrix is a tiny matrix on its own, and this is why the reason why we have that is because every method kind of have some parameter to tune. So for example, the length of the time step, or some threshold distance, and the color of the cell will tell us if the method succeeds or not. And we see that for something as simple as a tetrahedron falling in a plane, some methods have all green, so everything is fine, but something like the method which is called CCD here may generate intersection if we have a large time step and a small threshold distance, or something that could also blow up. And this is interesting because the scenes are particularly easy, and the bad thing here is that if you're unlucky with the choice of the parameter and you end up in a non-green cell, well, your simulation will break. And if you think back, what we wanted to do is have this black box thing, which is both for design and, for example, if you're inside an optimization pipeline, this is extremely bad, because if you have that parameter thing, the parameter set, it will not work and everything will just explode. And the moment we make the scene more and more complicated, for example, I don't know, 2 cubes falling on each other, there is almost no green anymore. Or if you start stacking more cubes, again we start having more and more problems. And this is also more complicated example, and we've moved with something more realistic, like for example a chainmail completely stuck, or a rod falling on a plane, or a cowhead bouncing around. Nothing is working reliably anymore. So the big question is why all these state-of-the-art methods are failing so heavily, and why there is so many problems. And well, one of the common problem I would say is that if you talk with people working in this field, what they want to do is to solve the collision with zero distance. So there is big assumption or big goal to say, well, when we have two objects colliding with each other, what we want is that at the very end they touch each other and they're zero distance, they're perfectly there. And this is really not physical. But before going there, I just want to tell you why this is a problem. In fact, if you have this separation, this zero distance that you want, you end up with a constraint optimization problem. And there are more or less two big rules to take there to solve this kind of constraint optimization problem. The first one, which is convergent, is we can allow the constraint to be violated and then try to come back and recover. The problem is there is no guarantee that you can actually recover from violating the constraint, so you end up in a situation where you have interpenetration. The other kind of approaches is we can try to enforce the constraint always to never let them violate it. This is less convergence and it can create problems. But even if you allow for that, because of numerical problem, we may end up violating the constraint numerically, and we end up having interpenetration. And you can imagine the moment there is some little bit of interpenetration, if you are integrating over time, so running a transient simulation, this interpenetration will become larger and larger and create more and more problems. And the biggest problem about interpenetration is their amount really depends on the setup. You can imagine that if you have large velocity in the beginning or large time step, it's more likely that stuff will interpenetrate and we'll have this problem. So now how we change that? So the main idea is that to change kind of mindset and never allow object to get closer to 10 to the minus 8. And in fact, this change of paradigm, this change of mentality makes the problem tractable, makes the problem tractable robustly, similarly to the envelope in tetrahedral meshing. So this 10 to the minus 8 may sound like a magic numerical constant, but in fact this 10 to the minus 8 is the space between atoms. So if you think about, you're trying to simulate these two objects and you really never want them to be so close, because the moment they get too close you start having atomic forces, and you can imagine if you're lancing a ball against a wall and the atoms start colliding to each other, you end up having different physics and nuclear reaction, which is exactly not what you want. But this change and not allowing stuff to get close, this allows to change the problem and transform the optimization into something that's solvable with Newton and a smooth barrier. So now we don't want object to get too close, so we just add a barrier which will prevent stuff, and which go to infinity, which will prevent stuff to get too close and prevent them to collide. And this change allows the problem to be casted into a Newton with a smooth barrier, which is something much easier and more tractable to solve than a constraint optimization problem. So with this change we can actually simulate something like a soft object like this dolphin passing through a really thin funnel. And this is important, there is no parameter tuning, we just set up the simulator with a significantly large time step, and in every step of this simulation there is no collision. The funnel and the dolphin are always completely separated. Complexity of the dolphin and funnel simulation. Here we have something even more complicated. We have this hairy ball which is bouncing and colliding against a piece of glass, and the time step here is also pretty large, 10 to the minus 3, and in the maximum time of this simulation we have something like 100,000 collision happening. And you see the whole thing looks really natural and physical. And you may think about that we change kind of our problem. Now we don't have anymore this hard constraint, this constraint optimization problem. We have this barrier. Are we really changing the physics? Are we still solving the same problem? So to validate and check that, what we did is take a recorded footage of a golf ball hitting a wall, match the material parameter and the boundary condition, so the initial velocity, and on this slide we are showing how our method is performing. And you see that it's perfectly in line and matches the reality really well. I just want to add a note that someone playing golf told me that this is not a real golf ball, this is a training ball. A real golf ball is much harder and doesn't deform too much. But nevertheless, the whole simulation, our simulation, matches reality pretty well, and you also see this shock wave propagating and the ball bouncing back. There is no restitution model, the bouncing back effect is just done by the ball deforming and relaxing back. One nice part about our reformulation of the problem is we can also handle codimensional object. So codimensional object is something where we can have something like 1D colliding with something 3D and etc. Everything, the only thing we need for our primitive is to be able to compute and evaluate the distances. So for example, we can have this ball falling or this piece of cloth falling on to the object. We also integrated a complete friction model with the same principles. So instead of solving the real difficult discontinuous friction model, we just smooth it out and have something similar to our barrier, so we can simulate something like a stack of cards falling on each other. Now, before concluding, let me give you a little bit of the limitations. So the method is not interactive, it's slow, but not much slower than existing state-of-the-art methods. Another thing is that we don't have any guarantee on energy preservation. Our experiment showed that there is some dissipation, which is good, but we cannot guarantee to maintain the friction. Another thing is, if you ever try to work with friction models, usually you have two states. One is when you're sticking and the other one when you're sliding, and there is a non-smooth transition. You just jump from one to the other one. Again, for the same reason, what we wanted to do is to make everything smooth and to be able to optimize for it. So we smoothed the friction model, so we smoothed the transition between the sticking and the sliding regime, and this is also not completely physical, but we again match with the experiment and it looks realistic enough. And finally, which is more related to this course in particular, we will be presenting in the next part a complete package of Python library to run simulation, to do geometric computing more in general, and this part about collision is new and is not yet integrated in the Python packages. We expect to develop it over the summer. So I think this is all for our black box analysis part. So thank you everybody for listening.
Let's go.
Okay, thank you everybody for being here and listening to our first part of this tutorial. So we try to answer the question directly into the different chat system. Are there other additional questions you wanted to ask only at the end? Let's wait a couple of seconds to see if there is something popping up. Okay, I'm not seeing any new questions, so this ends the first part of our tutorial. There are still two parts coming up, tomorrow and the day after tomorrow. Tomorrow we will have a big practical part on machine learning, so how to use this basic library we saw in the beginning, this libIGL, how to integrate that into a more complicated system with machine learning. And the day after tomorrow, we see how to integrate all the theory we saw today in the second part today. Again, how to integrate everything in Python, how to easily use all this fancy advanced simulation in Python. So there is a question on the YouTube channel. So there is a documentation for Polyfem. Yes, Polyfem has its own website, which is polyfem.github.io. I think this link is on the course website too. And more information will come on Wednesday about Polyfem and the Polyfem side in Python. So we can wait another couple of minutes to see if there is other question. So I don't see any dots moving in the different chat systems. So I think, yeah, and also see people dropping out of the YouTube channel. So I think this kind of conclude this first part. Okay, there is a new question coming in. Yes, so the geometric tolerance is an input. So you just decide whatever you want, let's say 10 to the minus 4 or 10 to the minus 3, and then the final mesh is guaranteed to have to not deviate more than that threshold from the input mesh. So this is an input parameter. And how do we verify it? Well, the current implementation uses sampling. So every face of the surface of the tetrahedral mesh is sampled. And this will guarantee that, well, the sample will be inside. We can just check it with a tree. We have just a recent work just published where we have an exact way of verifying that, and we are in the process of integrating this work into the mesher. So to have a real formal guarantee about the final surface not being too far from the input. Now we have a good heuristic.
And in general, like this parameter will control the density of a mesh and also the corresponding runtime of the entire simulation. So if like a larger tolerance will allow for more variation of the geometry and a coarser final mesh, so faster overall simulation, and the more you tighten this accuracy, the denser the mesh will be, and so the longer the simulation's time will also be. But it is something that the user can control, and it's something that should be tuned depending on the application that you're targeting. But it is still something that you pick per application. So after you know what you want to achieve, let's say for milling, and you decide to go for a tolerance of 50 micron, then any model that you want to process in this way can be processed automatically. Okay. I think if there are no more questions, this concludes the first day of the tutorial, and we are hoping to see you here tomorrow. I think we can close it here.